Hello there, and welcome to Science for Sleep, a quiet place where curiosity slows down, thoughts loosen their grip a little, and science takes the long way around so you do not have to rush anywhere at all. Wherever you are right now, whether you're stretched out in bed, resting on a sofa, or letting the day fade in the background while a small light glows nearby, you are exactly where you need to be for this moment. There is nothing you need to solve, nothing you need to remember, and nothing you need to prepare for. Just listening is enough. Tonight, we're going to spend some gentle time with something so familiar that it often goes unnoticed. Something that fills every room, spills through every window, and quietly follows you wherever you go. Light. Not as a switch you flip or a screen you stare into, but as something far stranger and more interesting than it first appears. We use it constantly without stopping to ask what it really is. We trust it to show us the world, to wake us in the morning, to guide us home after dark. And yet, when you slow down and look closely, light turns out to be one of the most puzzling things science has ever tried to understand. Before we go any further, take a moment to notice the light around you right now. Maybe it is dim and warm, coming from a lamp or a hallway down the way. Maybe it's the cool glow of a screen, or the faint spill of streetlights through a window, or perhaps the room is mostly dark with just enough light for shapes to exist without demanding attention. Where are you listening from tonight, and what kind of light is sharing the space with you? It is a simple question, but a fitting one. Light has always been tied to place, to time, to the feeling of being somewhere specific. If you find this slow exploration calming, interesting, or simply a pleasant way to unwind after everything the day has asked of you, you're very welcome to like the video or subscribe. It helps this small pocket of calm reach others who might need it too. There is no rush to decide. You can always think about it later. For now, just let the words arrive and pass, like light itself does. It might seem odd to devote so much attention to something that feels so obvious. Light is just there. You turn it on, you turn it off. It fills the gap between objects and your eyes, and that seems to be the end of the story. But that sense of obviousness is deceptive. For centuries, people argued about what light actually was. Some thought it must be a kind of substance flowing through space. Others believed it was a vibration of some invisible medium. Still others suspected it behaved more like a stream of tiny particles. Each idea worked well enough in some situations and failed completely in others, leaving behind a trail of confusion, debate, and surprisingly passionate disagreement. Long before equations and laboratories entered the picture, humans had a complicated relationship with light. Fire was one of the earliest forms of it that we learned to control, and with fire came warmth, safety, and the ability to push back the dark. The sun governed when people worked, rested, travelled, and gathered. Shadows became tools for telling time. The changing quality of daylight marked seasons, moods, and rituals. Light was practical, but it was also symbolic. It meant clarity, knowledge, life. Darkness, by contrast, meant uncertainty and rest, sometimes fear, sometimes peace. Even now, those old associations linger. We speak about seeing the light when something finally makes sense. We describe ideas as bright or dim. We talk about enlightenment, about being kept in the dark, about shining a light on a problem. All of that language grew out of the simple fact that without light, vision stops. And without vision, the world feels incomplete. Yet none of that tells us what light is made of. It only tells us what light does for us. Science, especially the slower, more careful kind, is often about separating those two questions. What does something do, and what is it really? Those answers do not always line up neatly. If you had asked a scientist a few hundred years ago what light was made of, you might have received an answer that sounded confident and reasonable at the time. Light, they might say, is a wave travelling through a medium, much like sound travels through air or ripples move across water. This idea had an appealing simplicity. Waves were familiar. They explained reflection, refraction, and the bending of light through glass. The only problem was the medium. If light was a wave, it needed something to wave through. Scientists invented an invisible substance called the ether to solve this problem, a hypothetical material that filled all of space, even the emptiness between stars. For a while this worked well enough. Then experiments became more precise, and the ether stubbornly refused to reveal itself. No matter how carefully scientists looked, they could not detect Earth moving through this invisible substance. Eventually the ether faded away, leaving behind an uncomfortable gap. Light behaved like a wave, but not like any wave anyone had ever encountered. Other experiments pointed in a completely different direction. Under certain conditions, light acted less like a smooth, spreading wave, and more like a series of discrete events, tiny packets delivering energy in specific amounts. This behavior made no sense if light was only a wave. It made much more sense if light consisted of particles. But particles came with their own problems. They did not easily explain interference patterns or the way light could cancel itself out in some places and reinforce itself in others. For a long time, science was stuck with an unsatisfying answer. Light seemed to be a wave when it was convenient and a particle when that worked better, refusing to commit to a single identity. This was not a matter of incomplete understanding that would soon be resolved with a clever experiment. It was a deep, structural problem that forced scientists to rethink some of their most basic assumptions about reality. As we move gently through this topic together, there is no need to hold all of that complexity in your mind at once. You do not need to remember names, dates, or equations. Think of this instead as a guided wandering, the kind where you follow a path not because you know where it leads, but because the walk itself is pleasant. Each idea will appear, settle for a moment, and then make room for the next one. One of the most surprising things about light is how fast it moves. Even without numbers, the scale is difficult to grasp. Light from the sun takes a little over 8 minutes to reach Earth. Light from distant stars can travel for years, centuries, or millions of years before finally arriving at your eyes. When you look at the night sky, you're not seeing things as they are now, but as they were long ago. Light is a messenger from the past, carrying information across enormous distances without slowing down or wearing out. That speed led many people to assume that light must be weightless, insubstantial, almost nothing at all. How could something so fast, so intangible be made of anything? And yet, light can push. This is not a metaphor. Light carries momentum. Under the right conditions, it can exert pressure, nudging objects ever so slightly. Solar sails, thin reflective sheets designed for space travel, use this pressure to move without fuel. Even in everyday life, the warmth you feel from sunlight is energy delivered to your skin by light itself. So here we already encounter a quiet contradiction. Light feels empty, but it carries energy. It feels immaterial, but it can push. It seems constant, but its behavior changes depending on how you observe it. These contradictions are not flaws in our understanding. They are clues. As you listen, you might notice your own attention drifting in and out. That is perfectly fine. Light does that too. It spreads, scatters, reflects, and sometimes slips past without leaving a strong impression. You do not need to follow every sentence closely. The general shape of the story is enough. At its most basic level, light is a form of energy that moves through space. That statement is accurate but incomplete. It is like saying that music is organized sound. True, but it does not capture the experience of listening, the structure of harmony, or the emotion carried by a melody. To understand what light is made of, we need to look at how it behaves, how it interacts with matter, and how it fits into the larger picture of the universe. Light does not require air, it does not require water, it does not even require the presence of atoms. It travels just as comfortably through the near vacuum of space as it does through your living room. This alone sets it apart from most other familiar phenomena. Sound needs something to vibrate. Heat usually moves through contact. Light is different. It is self-propagating, meaning it carries with it everything it needs to keep going. And yet, light is deeply connected to matter. It is produced when atoms change their internal energy. It is absorbed when electrons shift between allowed states. It reveals the structure of molecules, the composition of stars, and the movement of galaxies. Through light, we have learned what the universe is made of without ever touching most of it. That relationship between light and matter is one of quiet exchange. An atom emits light. Another atom absorbs it. Information moves without anything physically travelling between them in the way we usually imagine. No tiny beads fly through space like dust. No substance is transferred. And still, something real happens. This is where the idea of light being made of particles called photons begins to make sense, even if it feels counterintuitive. Photons are not particles in the everyday sense. They have no rest mass. They cannot be pinned down or slowed to a stop. They always move at the same speed. They do not age. They do not experience time. From the perspective of a photon, if such a perspective could exist, the moment of emission and the moment of absorption would be the same instant. That idea alone is worth pausing on. Light crosses the universe, but for light itself there is no journey, there is no duration. Emission and arrival collapse into a single event. This does not mean that time stops for the universe. It means that light occupies a strange position in the structure of reality, one that resists everyday intuition. As the night continues, we will return to this strangeness again and again, each time from a slightly different angle. For now, it is enough to notice that light is not built from solid pieces stacked together like bricks. It is not made of substance in the way wood or metal is. It is made of relationships, of interactions, of energy moving in quantized steps. You might find that as you listen, your thoughts begin to soften around the edges. Questions lose their urgency. Answers become less about certainty and more about coherence. That is a good state to be in for this topic. Light itself does not offer simple answers. It offers consistent behaviour, reliable outcomes, and just enough mystery to keep the mind gently engaged. Let the glow around you remain just as it is. The story of light is already present in the room, bouncing quietly off walls, passing through glass, resting briefly on your eyes before moving on. There is no need to chase it. At first glance, the question seems simple, almost too simple to deserve this much attention. What is light made of? It sounds like the kind of thing that should fit into a sentence or two, maybe a diagram in a textbook, a quick answer followed by a reassuring nod. But the longer people have sat with that question, the quieter and more persistent it has become. Not loud, not dramatic, just present. Like a thought that waits patiently in the background, resurfacing whenever you think you're finished with it. Light is everywhere, and that familiarity makes it easy to assume we already understand it. You flip a switch, the room brightens, the sun rises, shadows shorten, a screen lights up, and information pours out. All of this feels practical, reliable, and well-behaved. Light shows up on time. It does what it's supposed to do. It rarely surprises us in daily life. Yet behind that dependable surface is a question that refuses to settle. When light travels from one place to another, what exactly is moving? That question matters more than it first appears to. It is not just about light. It is about how we decide what counts as a thing in the first place. Most objects you encounter are easy to categorize. A chair is made of wood or metal. Water is made of molecules. Air is made of gases. Even things you cannot see, like sound, can be described as vibrations in something else. There is always a material basis, something underneath that carries the effect. Light does not fit comfortably into that pattern. There is nothing obvious underneath it, no medium you can point to, no substance left behind after it passes. You cannot scoop up light or bottle it in the usual sense, and yet you cannot dismiss it as nothing either. It carries energy. It carries information. It can heat surfaces, trigger chemical reactions, and move objects ever so slightly. Whatever light is, it is doing real work. The quiet question hiding inside light is not just what is it made of, but what does it mean to be made of something at all? That question tends to surface slowly, especially when the pace of thinking slows down. It is the kind of question that does not demand an immediate answer. It invites you to sit with it, to notice where your assumptions begin to blur. Consider how often we equate being real with being solid. We trust things we can touch. We believe in weight, texture, resistance. Light offers none of that. You can see it, but you cannot grasp it. You can feel its warmth, but not its edges. It fills a room without occupying space in the way furniture does. Two beams of light can cross paths without colliding, passing through each other as if neither were there. That behavior alone already sets light apart from most things you're used to thinking about. Two solid objects cannot occupy the same space at the same time. Light seems to do exactly that without complaint. It overlaps, interferes, combines, and separates again, all without leaving marks or dents. This makes it tempting to treat light as something less than fully real, like a visual effect rather than a physical presence. And yet, remove light entirely, and the world you experience collapses into something very different. Vision disappears, colours vanish, distance becomes guesswork. The structure of your surroundings becomes vague and uncertain. Light is not an optional extra. It is woven into how reality shows itself to you. So the question persists: what is actually there when light moves through space? Is something travelling, or is it more accurate to say that something is happening? One way to approach this is to think about how light behaves when it interacts with matter. When light strikes a surface, several things can happen. Some of it may be reflected, bouncing away at an angle that depends on the surface. Some may be absorbed, transferring energy into the material and warming it slightly. Some may pass through, perhaps slowed or bent along the way. These interactions are predictable, measurable, and repeatable. They follow rules. Rules imply structure. Structure suggests underlying reality. Light may be elusive, but it is not arbitrary. It behaves in consistent ways, and those behaviors can be described with remarkable precision. That consistency is one of the reasons scientists took the question of light so seriously. If light were merely an illusion, a trick of perception, it would not obey such strict mathematical patterns. As experiments became more refined, it became clear that light carries energy in specific amounts. This was not always obvious. Early theories treated light as something continuous, like a wave on water, smoothly varying in intensity. But certain experiments refused to cooperate with that picture. When light interacts with electrons in atoms, the energy exchange happens in discrete steps. Not any amount of energy is allowed, only certain values work. This was deeply unsettling at the time. It suggested that light does not deliver energy as a smooth stream, but as individual packets. These packets came to be called photons, not because the name solved anything, but because it gave scientists something to talk about. Naming a mystery does not remove it, but it does make it easier to examine. Calling light a stream of photons, however, introduces its own set of problems. Photons behave nothing like everyday particles. They have no mass at rest. They cannot be slowed down. They do not follow simple trajectories you can draw on a piece of paper. They do not even exist in the usual sense between interactions. They are created, absorbed, and in between, they occupy a strange conceptual space. If that sounds vague, it is because the reality is genuinely difficult to describe using everyday language. Our intuition evolved to deal with objects that move slowly, bump into each other, and stay put when not disturbed. Light does none of that. It is not surprising that it resists easy description. Another way to approach the question is to ask whether light needs to be made of something at all. Perhaps that expectation itself is misplaced. Perhaps light is not a thing in the same category as tables and stones. Perhaps it is a process, a pattern of change, a relationship between electric and magnetic fields that sustains itself as it moves. This idea brings us closer to how modern physics often describes light. Light can be understood as an electromagnetic disturbance, a linked oscillation of electric and magnetic effect that propagates through space. No medium required, no substance flowing, just a pattern that maintains itself. But even this description raises questions. What exactly is oscillating? Electric and magnetic fields are not made of matter either. They are properties of space, conditions that describe how charged particles would behave if they were present. Saying that light is made of fields feels like replacing one mystery with another. At this point, it may be helpful to notice that the discomfort you might feel around these ideas is not the failure of understanding. It is a signal that you are brushing up against the limits of familiar categories. Light forces you to loosen the grip on the idea that everything must be made of tiny solid pieces. There is a quiet shift that happens when you allow for that. The world becomes less like a collection of objects and more like a network of interactions. Things are defined not only by what they are, but by how they relate to everything else. Light fits naturally into that picture. It is not an isolated object, it is a connector. When light leaves a source, it carries information about that source. Its colour tells you something about temperature or composition. Its intensity tells you something about distance or power. Its direction tells you where it came from. In this sense, light is a messenger. It links events across space and time, and this brings us back to the quiet question. If light is a messenger, what is the message written on? What is the medium of information? One answer is that the message is written on the structure of the universe itself. Space is not empty in the way an empty box is empty. It has properties. It allows certain kinds of motion and forbids others. Light moves through space not because space is filled with something, but because space itself supports the behavior we call light. That idea can feel abstract, but it becomes more approachable if you think about other familiar patterns. A wave on a stadium crowd is not made of a substance that travels around the stands. People stand up and sit down in sequence, and the pattern moves. Nothing physical makes the full loop. The wave exists because of coordinated local actions. Light, in some interpretations, is similar. It is a coordinated pattern of change that moves through the structure of space. Nothing needs to travel the whole distance for the effect to propagate. Still, unlike a stadium wave, light carries energy. It can do work. That energy is not borrowed or symbolic. It is measurable and conserved. This is where the photon picture regains its usefulness. Photons give us a way to account for energy transfer without imagining a substance sloshing through space. So is light made of photons? Yes, and also no, depending on what you mean by made of. Photons are not building blocks in the usual sense. They are not smaller pieces that can be broken apart. They are indivisible events, interactions between light and matter that come in discrete units. You might think of photons less as objects and more as transactions. An atom emits a photon. Another atom absorbs it. The photon is the accounting entry that balances the energy books. In between, its existence is described mathematically, not materially. This perspective helps explain why light sometimes behaves like a wave and sometimes like a particle. Waves describe how probabilities spread out. Particles describe how interactions happen. Light is not switching identities. It is obeying a deeper set of rules that do not map cleanly onto either category. If this feels like an unsatisfying answer, that is understandable. Human curiosity often wants a clear picture, something you can imagine easily. Light does not offer that. It offers consistency instead. No matter how strange the description sounds, the predictions work. Experiments confirm them again and again. There is a quiet humility in accepting that some things are real, even if they do not fit neatly into mental images. Light invites that kind of acceptance. It does not demand that you fully grasp it in order to benefit from it. It simply continues to do what it does. As you listen, you might notice the way light in your environment has likely changed since we began. Perhaps your eyes have adjusted to the dimness. Perhaps the glow feels softer now. Light is interacting with you continuously, shaping your experience moment by moment without asking for attention. The question hiding inside light remains open, not because science has failed, but because the question itself keeps evolving. As our understanding deepens, the language changes. What once seemed like a demand for substance becomes a question about structure, interaction, and information. Long before light became something you could summon with a fingertip, long before glass bulbs hummed quietly and ceilings or screens glowed patiently in pockets, light arrived only when nature allowed it. It was not constant. It was not guaranteed. It appeared and disappeared on its own schedule, and people learned to shape their lives around its presence and its absence. In that older world, light was not a background condition. It was an event. Imagine a time when night was truly dark, not dim, not gently illuminated by distant cities or passing cars, dark in a way that erased edges and swallowed distance. When the sun went down, vision narrowed to what little light the moon and stars could offer, and even that depended on weather, season, and chance. Clouds could take the sky away entirely. A new moon could leave the land almost featureless. In those conditions, light was not taken for granted. It was watched, protected, and deeply valued. Fire was the first form of light humans learned to control, and that control changed everything. A flame was more than brightness. It was warmth, protection, and a signal that life was present. Fire pushed back predators. It extended waking hours. It created a shared center where people gathered, talked, worked, and rested. Light, through fire, became social. But fire was also demanding. It required fuel. It needed attention. It could grow dangerous if neglected. Its light flickered, shifted, and cast moving shadows that made familiar spaces feel alive and unpredictable. That flicker was not just visual noise. It shaped how early humans experienced the world after sunset. Shape seemed less fixed. Movement felt ambiguous. The boundary between what was there and what might be there blurred easily. In that environment, light was not neutral. It carried emotion. Warm firelight meant safety. Sudden darkness meant vulnerability. A distant glow might signal another group, a threat, or an opportunity. Light was information long before it was understood as energy. Above the fire was the sky, the second great source of light that shaped early understanding. The sun was not just bright. It was reliable. It rose and set with enough regularity that entire systems of timekeeping, agriculture, and ritual grew around it. The sun's movement divided the day into usable segments. Morning brought activity. Evening brought rest. Light structured behavior. The moon offered a different kind of light. Softer, colder, changing its shape over weeks rather than hours. It illuminated the night unevenly, sometimes generously, sometimes barely at all. Its cycles became markers of longer time. Months took shape. Tides responded. Animals adjusted their behavior. The moon taught people that light itself could change without disappearing. Stars added another layer. They were distant, fixed patterns that returned night after night, year after year. Unlike fire or the moon, they were unreachable. Their light arrived silently, steady and cold, from places no one could visit. Even without knowing what stars were, people understood that their light was old. It had been travelling long before it reached the ground beneath bare feet. In this pre-electric world, light was never uniform. It came in qualities. Firelight was warm and unstable. Sunlight was bright and directional. Moonlight was diffuse and uncertain. Starlight was faint but constant. Each type of light shaped perception differently. Colours shifted, depth changed. Movement was emphasized or lost depending on the source. Because of this, early humans did not experience a single version of the world. The same landscape looked different at noon, at dusk, by firelight and under stars. Light was not just revealing objects. It was actively shaping reality as it was perceived. This matters when thinking about what light is made of, because before theories and measurements, light was known through experience. People noticed how it behaved without naming why. They saw that firelight danced while sunlight did not. They saw that shadows stretched and shrank. They noticed that certain stones sparkled, that polished surfaces reflected, that water bent light in strange ways. These observations laid the groundwork for later questions, even if they were not framed scientifically. Why does light travel in straight lines until it doesn't? Why does it bounce off some surfaces and soak into others? Why does it break into colours after rain? These questions did not require microscopes or equations. They arose naturally from living in close contact with light's behaviour. Fire, in particular, taught an early lesson about light and matter. Flames produced light when fuel was consumed. Something was clearly happening at the material level. Wood burned, and light appeared. The connection between physical change and light emission was obvious, even if unexplained. Light seemed to be released from matter under the right conditions. This association lingered. For a long time, light was thought of as something that came out of objects, almost like a subtle substance that escaped when matter was excited, heated, or disturbed. That intuition was not entirely wrong. Modern physics still describes light as being emitted when atoms change energy states. The difference is that we now describe the process more precisely. The sky, meanwhile, offered a different puzzle. Sunlight arrived from above, constant and overwhelming. Unlike fire, it did not appear to consume fuel, at least not in any visible way. The sun rose every day without burning out. Its light did not flicker. It illuminated everything equally. This made it feel less like a process and more like a condition of existence. Many early cultures treated sunlight as fundamental, as something that sustained life directly. Crops grew toward it. Bodies warmed under it. Days revolved around it. Light was not separate from life. It was intertwined with survival. This intimate relationship meant that light was rarely questioned in abstract terms. It was accepted as a given feature of the world, like gravity or air. The idea that light itself might be made of something or governed by hidden rules was not obvious. Why question something so constant? Still, curiosity found its way in through small cracks. Rainbows were one such crack. They appeared suddenly, vivid and temporary, showing colours that did not normally exist in the sky. They did not belong to objects. They had no clear source. Light seemed to split itself apart, revealing complexity where uniform brightness had been assumed. Shadows were another source of quiet questioning. They were not objects, yet they had shape. They moved when the light moved. They distorted reality without touching it. A shadow could grow, shrink, stretch, or disappear depending on the position of a light source. This suggested that light had geometry, that it interacted with space in rule-based ways. Reflections added to the mystery. A smooth surface could create a second world, inverted and unreachable. The reflected light carried full detail, yet the image could not be touched. This hinted that light could preserve information about objects without being the object itself. All of these experiences built an intuitive understanding of light long before formal science. Light was consistent but not simple, reliable but not dull. It followed patterns that could be learned, even if they could not yet be explained. When artificial lighting eventually expanded beyond fire, first through oil lamps and candles, then gas, and finally electricity, something subtle changed. Light became stable, shadows softened, darkness retreated. The world stopped transforming so dramatically between day and night. Light became background rather than event. This shift made it easier to forget how strange light really is. When illumination is always available, its absence becomes the anomaly rather than its presence. The mystery fades into convenience, but the ancient experience still matters. It reminds us that light is not just a utility, it is a phenomenon that shaped human perception, behavior, and curiosity long before anyone asked what it was made of. The question did not arise in a laboratory. It arose around fires, under skies, and in the slow noticing of patterns. As you rest with this idea, you might consider how different light sources still affect you emotionally. Warm light often feels calming. Harsh light can feel intrusive. Natural light shifts mood and energy in ways that are hard to ignore. These reactions are echoes of a much older relationship. Light does not just enter the eyes, it enters the nervous system. It regulates sleep, alertness, and internal timing. Long before it was measured in wavelengths or described with equations, light was shaping bodies from the inside. There was a time when the idea that light travelled at all was not obvious. It sounds strange now because movement feels like such a basic property. We see light leave a source and arrive somewhere else, so of course it must move. But for much of human history, light was thought to appear instantaneously. You opened your eyes, and the world was simply there. You lit a fire, and the glow filled the space without delay. There was no visible journey, no sense of motion in between. This assumption made intuitive sense. Everyday experience offered no hint of a pause between cause and effect. Strike a spark, and light appears. Look toward the horizon, and distant mountains are visible immediately. Nothing in ordinary life suggested that light took time to get anywhere. If it did move, it must have moved infinitely fast. That idea persisted for centuries, not because it was tested and confirmed, but because it was rarely questioned. When something works seamlessly, it tends to fade into the background. Light revealed the world so effectively that its own behavior escaped scrutiny. The first cracks in this assumption appeared not through deliberate experiments, but through careful observation of the sky. Astronomy has always had a way of stretching human intuition, forcing patience where immediacy feels natural. When people began to watch the heavens closely, patterns emerged that did not quite fit with the idea of instantaneous light. One of the earliest hints came from observing eclipses and planetary motion. If light were truly instantaneous, all visible changes should line up perfectly with their causes. But as measurements improved, small discrepancies appeared. They were subtle, easy to dismiss at first, but persistent enough to provoke curiosity. A more decisive moment arrived in the 17th century, when astronomers began tracking the motion of Jupiter's moons. These moons followed predictable orbits, disappearing behind the planet and re-emerging on the other side at regular intervals. Or at least they should have. What observers noticed was that these intervals were not perfectly regular. When Earth was closer to Jupiter, the moons seemed to appear slightly earlier than expected. When Earth was farther away, their appearances lagged behind predictions. The moons themselves had not changed their behavior. Something else was introducing a delay. The explanation that eventually emerged was quietly revolutionary. Light, it turned out, was not arriving instantly. It was taking time to cross the additional distance when Earth was farther away. The delay was small, only minutes, but it was measurable. For the first time, light had been caught in the act of travelling. This realization carried profound implications. If light had a speed, then it was not just a condition of visibility. It was a physical phenomenon with measurable properties. It could be timed. It could be delayed. It could, in principle, be compared to other kinds of motion. Once the idea took hold, scientists began trying to measure that speed more directly. Early attempts were crude by modern standards, relying on rotating mirrors, distant observers, and clever timing tricks. But even with limited tools, the conclusion became unavoidable. Light moved extremely fast, but not infinitely so. This speed was astonishing. It dwarfed anything humans could achieve mechanically. Cannonballs, arrows, even sound itself moved sluggishly by comparison. Light raced ahead, crossing vast distances in fractions of a second. And yet, it still took time. That combination of near incomprehensible speed and finite travel was unsettling. It challenged the comfortable assumption that seeing was immediate. The moment light was understood to travel, the nature of space itself began to change. Space was no longer just a passive backdrop. It became something that light crossed, something that could introduce delay, separation, and structure. Distance mattered in a new way. At the same time, the idea of light travelling raised an immediate follow-up question. If light moves, what is moving? A wave must move through something. A particle must move through space. Which one was light? Early thinkers often favoured the wave idea. Waves were familiar. Sound was a wave in air. Ripples were waves on water. It seemed reasonable that light might be a wave as well, moving through some subtle, invisible medium that filled all of space. This hypothetical medium came to be called the ether. It was imagined as weightless, transparent, and everywhere. It had to be incredibly stiff to support the immense speed of a light, yet completely undetectable to touch or motion. It had to pass through matter effortlessly, while remaining fixed enough to define an absolute frame of reference. The ether was not introduced casually. It was an attempt to preserve intuitive ideas about motion and waves. If light was a wave, then something had to be waving. The ether filled that role. For a long time, this idea felt satisfying. It explained how light could travel through empty space. It allowed scientists to apply familiar wave mathematics. It fit neatly into existing frameworks. But there was a problem. No matter how carefully scientists looked, the ether refused to reveal itself. Earth's motion through space should have produced detectable effects, subtle shifts in the speed of a light depending on direction. Experiments were designed to catch these effects. They failed again and again. Light behaved as if there were no ether at all. Its speed remained the same in every direction, regardless of Earth's motion. This was not a small inconvenience. It was a direct contradiction. At this point, the story of light travelling took an unexpected turn. Instead of modifying the ether to fit the data, some scientists began to question the assumption that a medium was required at all. Perhaps light did not need something to travel through. Perhaps it was fundamentally different from sound or water waves. This shift marked a deeper change in thinking. It required letting go of the idea that all motion must be motion of something through something else. Light seemed to propagate itself, carrying its own structure along with it. The concept of electromagnetic waves offered a new way forward. Electricity and magnetism, once thought to be separate forces, had been unified into a single framework. Changes in electric fields produced magnetic effects, and changes in magnetic fields produced electric effects. These linked oscillations could sustain themselves and move through space. Light, in this view, was an electromagnetic wave. It did not need a medium because the fields themselves were the medium. Space was not empty in the traditional sense. It had properties that allowed these fields to exist and interact. This was a radical idea, but it worked. The mathematics predicted a specific speed for electromagnetic waves, and that speed matched the measured speed of light. The conclusion was unavoidable. Light was an electromagnetic phenomenon, and yet even this elegant solution did not settle everything. Waves spread out, they interfere, they can overlap. Light did all of these things, but light also behaved in ways waves should not. When light struck certain materials, it ejected electrons, but only if its frequency was high enough. Increasing intensity did not help if the frequency was too low. This behaviour made no sense in a purely wave-based picture, where energy delivery should depend smoothly on amplitude. To explain this, the idea of light being quantized re-emerged, this time with experimental backing. Light energy came in discrete packets. These packets were later called photons. Here, the notion of a light travelling became more nuanced. Light did not travel as a stream of tiny bullets, nor as a continuous wave in the everyday sense. It travelled as a probability distribution, a structured pattern that governed where and how interactions could occur. Between emission and absorption, light followed wave-like rules. At the moment of interaction, it behaved like a particle. This was not a contradiction to be resolved later. It was a feature of how nature operates at small scales. Understanding this required a new way of thinking about motion itself. Light did not move through space the way objects do. It did not occupy positions in the same way. Asking where a photon was at a given moment was often the wrong question. Instead, light's travel was described by the evolution of fields and probabilities. The mathematics tracked how likely interactions were at different locations and times. The path was not a line, but a spread, a set of possibilities constrained by rules. Despite this abstraction, the consequences were concrete. Light took time to travel. That time could be measured, it could be affected by gravity, it could be stretched by motion. It was no longer just a messenger. It was woven into the structure of space and time themselves. One of the most profound implications of light's finite speed is that seeing is always seeing the past. The delay is usually tiny, far below awareness, but it is always there. When you look at an object across the room, the light reaching your eyes left it a fraction of a microsecond earlier. When you look at the sun, the delay is minutes. When you look at distant stars, it can be millions of years. This means that light does not simply reveal reality, it reveals history. Every act of seeing is an act of receiving information that has already travelled. This realization subtly changes the meaning of observation. You're not accessing the present state of distant objects. You're accessing a record carried by light across space and time. The universe, in this sense, is constantly communicating with itself through light. As tools improved, scientists learned to use this property deliberately. By analysing the light from stars and galaxies, they could determine composition, motion, temperature and distance. Light became a probe, a way to learn about places no one could ever visit. None of this would be possible if light did not travel. Its motion is not an incidental feature. It is the reason light can function as information at all. Yet, the question of what exactly moves when light travels remains subtle. Energy moves, momentum moves, information moves. But a photon, as an object, does not travel through time in the way you do. It does not experience duration. This strange property sits quietly beneath all of modern physics. Light connects events without itself aging. It links moments without belonging fully to either one. As you listen to this, light is continuing to do this work effortlessly. Signals are passing from a source, reflecting off surfaces, entering your eyes, triggering cascades of activity in your nervous system. All of that depends on light's ability to move, and still, the movement is unlike any other. Light does not slow down, it does not speed up. It always moves at the same pace, regardless of the motion of the source or the observer. This invariance forced a rethinking of space and time themselves, but that story unfolds gradually, and there is no need to rush into it. For now, it is enough to notice that there was a moment, historically speaking, when light was first recognized as something that travelled. That recognition transformed light from a static presence into a dynamic participant in the universe. Once the idea that light travelled began to settle into place, another question followed almost immediately, and it was a question shaped by familiarity. If light moves, then how does it move? For most of human experience, motion that spreads outward follows a pattern we already understand. Drop a stone into a pond, and ripples expand in neat circles. Clap your hands and sound waves fan out through the air. Shake a rope and waves travel along its length. In every one of these cases, something moves because something else is being disturbed. Water moves up and down, air compresses and relaxes, the rope shifts its position. A wave, in everyday terms, is never just a wave. It is always a wave of something. So when scientists began to seriously consider that light might be a wave, they did so almost by reflex. Waves were familiar. Waves explained spreading, bending, interference, and patterns of brightness and darkness. Many of light's behaviours fit comfortably into this framework. Shine light through a narrow opening, and it spreads out. Pass two beams close together, and they interfere, creating alternating bright and dark regions. These were classic wave signatures. But very quickly, an uncomfortable detail made itself known. Light moved through empty space, not just thin air but near perfect vacuum. Sound could not do this. Water waves could not do this. Rope waves could not do this. Every known wave needed a medium. Light did not seem to care whether one was present. To resolve this, scientists proposed something that, at the time, felt reasonable. Space itself must be filled with a medium, one so subtle that it did not interact with matter in obvious ways. This medium would support light waves just as air supports sound. It would be everywhere, filling even the emptiest regions between stars. It would be invisible, intangible, and undetectable by ordinary means. This was the ether, not the mystical substance of myth, but a carefully imagined physical entity designed to solve a specific problem. The ether had to be incredibly stiff to allow light to travel so fast, yet offer no resistance to planets moving through it. It had to exist everywhere but leave no trace. It had to be perfectly transparent and perfectly stationary. For a while the ether did its job. It allowed light to be treated as a wave without forcing scientists to abandon familiar intuitions. Equations worked. Predictions lined up with observations. The idea settled into textbooks and lectures. But something about it never sat quite right. The ether was never observed directly. Every attempt to detect Earth's motion through it failed. Experiments designed to measure slight differences in light speed depending on direction returned the same result every time. Light behaved as if there were no preferred frame of reference, no hidden medium setting the stage. At some point, the simplest explanation became the most radical one. Perhaps light did not need a medium at all. Perhaps the assumption that waves require something to wave through was the real problem. This was not an easy leap to make. It required loosening a deeply held association between waves and matter. It meant accepting that there could be waves that were not waves of anything tangible. Waves that existed as patterns rather than motions of substance. The breakthrough came with the understanding of electricity and magnetism. These forces, once treated as separate, were revealed to be deeply linked. A changing electric field produced a magnetic field. A changing magnetic field produced an electric field. Together, they formed a self-sustaining system. If an electric field changed in time, it generated a magnetic response, which in turn generated an electric response, and so on. This chain reaction did not require a medium in the traditional sense. The fields themselves carried the structure. The disturbance propagated because the laws governing these fields allowed it to. Light, in this framework, was an electromagnetic wave. It consisted of oscillating electric and magnetic fields, locked together, moving through space. Nothing physical needed to wiggle. The wave was not a motion of matter, it was a motion of influence. This idea answered many questions at once. It explained why light could travel through empty space. It explained why light always moved at the same speed. It unified optics with electricity and magnetism. It replaced the ether with a deeper understanding of space itself. And yet calling light a wave still carries baggage. When most people hear the word wave, they picture water or sound or a rope. These images are helpful but misleading. They smuggle in assumptions that do not apply. An electromagnetic wave does not consist of peaks and troughs in a substance. Nothing is piling up and falling back down. Instead, the wave describes how the strength of electric and magnetic fields varies from place to place and moment to moment. These fields are not material objects. They are properties assigned to points in space, descriptions of how charged particles would behave if they were present. When we say a field oscillates, we're not saying that something physically sways back and forth. We're saying that the influence changes in a regular way. This makes electromagnetic waves harder to visualize, but easier to accept conceptually once you let go of the need for a physical medium. The wave is the pattern. The pattern is real. One way to approach this is to think in terms of information rather than substance. A wave is a way information moves. In sound, the information is carried by air molecules bumping into each other. In light, the information is carried by the structured evolution of fields. That structure can exist even in emptiness. Space is not nothing. It has properties. It allows fields to exist. It allows interactions to propagate. Light takes advantage of that. When light spreads out from a source, it does so according to precise rules. Its intensity decreases with distance. Its wavefronts expand. Its phase evolves. All of this can be calculated, predicted, and confirmed. Interference, one of the most wave-like behaviors of light, offers a particularly clear window into this. When two light waves overlap, their fields combine. In some places, they reinforce each other, producing brightness. In others, they cancel, producing darkness. Nothing material disappears in the dark regions. The fields simply add up to zero. This behavior is difficult to reconcile with a particle-only picture. It makes perfect sense in a wave description, and yet, as comfortable as this explanation is, it is not the whole story. Light does not always behave like a smooth, spreading wave. When it interacts with matter at small scales, it behaves in discrete ways. Energy is exchanged in fixed amounts. Individual detection events appear as localized hits, not smeared patterns. This duality does not mean that light switches personalities. It means that the wave description and the particle description are both limited perspectives on a deeper reality. The wave describes how possibilities spread. The particle describes how outcomes occur. Between emission and detection, light behaves like a wave. At the moment of interaction, it behaves like a particle. Neither description is sufficient alone. Still, the wave picture remains essential for understanding how light moves. It explains why light bends when it passes through different materials. It explains diffraction, polarization, and the entire structure of optics. Without waves, lenses would not work, rainbows would not form, interference patterns would not exist. What makes light unusual is not that it behaves like a wave, but that it behaves like a wave without water, without air, without anything familiar to carry it. It is a wave of fields, and fields are not objects you can point to. They are rules written into the fabric of space. This realization quietly reshapes the notion of what it means for something to move. Movement does not always require a thing to change position. Sometimes it is the pattern that moves, not the pieces. Think of a stadium wave again. No single person travels around the arena. The pattern does. Light is similar but even more abstract. There are no people standing up and sitting down. There is only the pattern. This helps explain why light can pass through light. Two beams cross paths without scattering or colliding. Their fields simply add together and continue on. There is no traffic jam, no interference unless conditions allow it. It also helps explain why light can be polarized. The oscillations of its fields can be oriented in particular directions. This orientation affects how light interacts with materials, how it reflects, how it transmits. None of this requires a medium with fibers or grain. It arises from the geometry of fields themselves. As you listen, light continues to do all of this quietly. Waves of influence pass through the room, through walls, through air, through your body. They are mostly ignored, filtered out by your senses, except where they matter. Your eyes respond to a narrow slice of these waves, converting them into signals your brain can interpret. Outside that slice, light still exists, invisible but active, carrying energy, information, and structure. The idea of waves without water is one of those conceptual shifts that feels small at first and then keeps expanding. It suggests that the universe is not just made of stuff, but of patterns that can exist independently of substance. Light is one of the clearest examples of this, and yet, even this understanding does not fully answer the question of what light is made of. Fields describe behavior, not composition. They tell us how light moves, not what it ultimately is. For a long time, the wave description of light felt like a triumph. It explained bending, spreading, interference, reflection, refraction, and the quiet elegance of optics. It fit neatly with the idea that light was an electromagnetic disturbance moving through space. Many scientists were content to stop there, but nature rarely allows a single story to remain complete for long. There were details that refused to settle, small inconsistencies at first, then stubborn contradictions that grew harder to ignore. These contradictions did not appear in sweeping cosmic observations or distant astronomical measurements. They appeared in controlled laboratory settings, in experiments that examined how light interacted with matter at very small scales. Places where intuition is often least reliable, and where reality tends to behave in ways that feel slightly unreasonable. One of the earliest and most unsettling clues came from studying how light transfers energy. If light were purely a wave, then increasing its intensity should increase the energy it delivers smoothly and continuously. Brighter light should always mean more energetic effects, but this was not what experiments showed. When light struck certain metals, it could eject electrons from their surface. This phenomenon, later called the photoelectric effect, behaved in a very particular way. Below a certain frequency, no electrons were ejected at all, no matter how intense the light was. You could flood the metal with low-frequency light and nothing would happen. Increase the frequency just enough, and suddenly electrons began to appear, immediately, even at low intensities. This was deeply confusing. According to wave theory, energy depended on amplitude, not frequency. Brighter light should have done the job regardless of colour, but reality disagreed. Energy seemed to arrive in discrete chunks, tied to frequency, not smooth waves of accumulation. The implication was unsettling. Light did not deliver energy continuously. It delivered energy in packets. Each packet carried a specific amount of energy determined by the light's frequency. If that packet did not contain enough energy, no interaction occurred. This was not a small correction. It was a fundamental challenge to the idea of light as a purely spreading wave. Something else was going on. To explain this behavior, the concept of light particles returned, but not in the old simplistic sense of tiny glowing bullets. These particles, later called photons, were strange from the start. They did not behave like ordinary matter. They had no rest mass. They always moved at the same speed. They could not be subdivided, and yet they behaved as discrete carriers of energy and momentum. Calling them particles was convenient, but misleading. Photons did not sit still. They did not occupy fixed positions. They did not follow definite paths in the way thrown objects do. They appeared when energy was emitted and vanished when energy was absorbed. Between those events, their behavior was best described by probability, not trajectory. Still, the particle idea explained something the wave picture could not. It explained why interactions happened in jumps rather than smears. It explained thresholds. It explained why light sometimes acted like a series of individual impacts instead of a continuous wash. At first, this dual description felt like a temporary compromise. Perhaps light was really a wave, but matter forced it to behave as if it were particle-like during interactions. Or perhaps light was really a particle, but many particles together produced wave-like patterns. Both explanations were attempted. Neither fully worked. What gradually became clear was that light did not fit into the classical categories at all. It was neither wave nor particle in the everyday sense. Those were metaphors borrowed from familiar experience, and light was politely ignoring their limitations. The idea that light consists of photons does not mean that photons are tiny objects flying through space like dust. A photon is better understood as a quantum of interaction. It is the smallest possible unit in which light can exchange energy with matter. When an atom emits light, it does not dribble energy outward continuously. An electron inside the atom shifts from one allowed energy state to another. The difference in energy between those states is released as a photon. That photon carries exactly that amount of energy, no more and no less. Likewise, when light is absorbed, an electron must absorb a whole photon at once. It cannot take half. It cannot borrow a little now and the rest later. The interaction is all or nothing. This discrete behavior is where the particle language earns its keep. It gives us a way to talk about these indivisible events. But it does not mean the photon is a tiny marble travelling along a track. Between emission and absorption, the photon does not have a well-defined position. Asking where it is at a given moment is often meaningless. What can be described is the probability of where it might be detected if an interaction occurred. This probabilistic spread behaves exactly like a wave. It diffracts, it interferes, it spreads out over space. The wave description tells us how the probability evolves. The particle description tells us what happens when probability collapses into an actual event. This is why light refuses to sit still. It cannot be pinned down to a single identity. It exists as a moving pattern of possibilities until an interaction forces a decision. Experiments that send individual photons through slits make this behavior impossible to ignore. Fire photons one at a time toward a barrier with two openings and detect where they land. Each photon arrives as a single point, a localized event, but after many photons an interference pattern emerges, identical to what a wave would produce. Each photon behaves as if it interferes with itself, not by splitting into smaller pieces, but by existing as a spread of possibilities until detection. There is no classical picture that makes this comfortable. It is simply how light behaves. The phrase particle begins to feel inadequate here. Particles, as we usually imagine them, have positions and velocities. Photons have momentum and energy, but position is a fuzzy concept until interaction. They are not objects moving through space so much as events unfolding in space-time. This becomes even stranger when considering that photons do not experience time. According to relativity, time slows down as speed increases. For something moving at the speed of light, time effectively stops. From the photon's perspective, if such a perspective can be defined, emission and absorption are the same instant. This means that while light may travel billions of years from a distant galaxy to your eye, the photon itself does not age. There is no journey. There is only connection. This property reinforces the idea that photons are not travelers in the usual sense. They are links between events. They connect changes in energy across space-time without themselves undergoing change. Calling this a particle stretches the word beyond its original meaning. But abandoning the word entirely would make communication difficult, so it remains, with the understanding that it carries caveats. Light's refusal to sit still also shows up in how photons behave in groups. They can bunch together or spread out depending on conditions. They can be entangled, meaning the behavior of one becomes linked to another even across large distances. They can interfere collectively or behave independently. These behaviors are not properties of classical particles. They belong to quantum entities, where individuality and separateness are not as clear-cut as intuition expects. Another sign that photons are not ordinary particles is their inability to exist at rest. You cannot trap a photon and hold it still. You can confine light between mirrors, bounce it around, slow it down in certain materials, but the photon itself always moves at the same fundamental speed. What changes is how often it interacts. This distinguishes light sharply from matter. Matter can be stationary. It can pile up. It can form structures that persist. Light does not settle. It does not accumulate in the same way. It is always in motion or gone. Yet despite this restlessness, photons obey strict conservation laws. Energy is conserved. Momentum is conserved. Interactions balance precisely. There is no fuzziness in the accounting, only in the paths between accounts. This blend of precision and uncertainty is characteristic of quantum behavior. Light was one of the first places where this behavior became undeniable. It forced a reconsideration of what it means for something to be made of something. If light is made of photons and photons are not material objects, then made of must mean something different. It cannot mean composed of smaller pieces in the traditional sense. It must mean structured by rules that allow discrete interactions. Light in this view is made of allowable actions, emissions, absorptions, transfers of energy and momentum that occur only in specific units. The photon is the name we give to one such unit. This perspective dissolves the conflict between waves and particles. The wave describes how the possibility of interaction spreads. The particle describes the interaction itself. Both are necessary. Neither is sufficient alone. As you rest with this idea, it may feel less like an answer and more like a reframing. The question shifts from what is light made of to how does light behave when it exists? Composition gives way to process. Light does not sit still because it cannot. It is defined by motion, by connection, by transfer. Even when confined, it is restless, bouncing, interacting, waiting for absorption. This restlessness is not chaos. It is structured, predictable, governed by laws that are astonishingly precise. The unpredictability lies not in outcomes as a whole, but in individual events. By the time scientists were forced to accept that light behaved both like a wave and like a particle, there was a growing sense that something deeper was being uncovered, something that did not fit into the old boxes at all. The problem was no longer deciding which description was correct. The problem was understanding how both could be true at the same time without cancelling each other out. Light was not politely choosing one role depending on circumstances. It was following rules that made both descriptions incomplete on their own. This is where the idea of a compromise enters, though compromise may not be quite the right word. It suggests negotiation, a middle ground, a blending of two familiar things. What light actually revealed was not a midpoint between waves and particles, but a framework in which those concepts were no longer fundamental. They became tools, useful in certain situations, misleading in others. To see why this was necessary, it helps to look carefully at what waves and particles represent in everyday thinking. A wave, in the classical sense, is extended. It occupies space. It spreads out. It can overlap with other waves and interfere. A particle, by contrast, is localized. It exists at a specific place at a specific time. It collides. It transfers energy in discrete impacts. Light stubbornly displays both sets of behaviors, but never all at once in a way that satisfies classical intuition. When light is traveling freely, spreading out from a source, bending through openings, forming interference patterns, the wave description works beautifully. When light interacts with matter, knocking electrons loose, triggering chemical reactions, or registering as a single detection on a sensor, the particle description becomes unavoidable. Early attempts to reconcile this often tried to keep one description primary and treat the other as an illusion. Some argued that light was really a wave, and particles were just artifacts of how matter responded. Others argued the opposite, that light was really made of particles, and waves emerged statistically when many particles were involved. Neither approach held up under scrutiny. Single photons produced interference patterns. Individual detection events obeyed wave-based probability distributions. The behavior did not depend on large numbers smoothing things out. It was intrinsic. This forced a conceptual shift that went far beyond light. It required rethinking what physical descriptions are meant to do. Instead of picturing what light is, physicists began focusing on what light allows to happen, and how likely different outcomes are. In this new framework, the wave is not a physical ripple moving through space. It is a mathematical object that encodes probabilities. It tells you where light might interact if it does. It evolves smoothly, spreading and interfering according to precise rules. But it does not represent something directly observable. The particle, on the other hand, represents the observable event itself. A click in a detector, a spot on a screen, an electron ejected from a surface. These events are localized and discrete. They are what you actually measure. The strange compromise is that both descriptions are necessary, but they apply to different aspects of the same phenomenon. The wave governs potential. The particle marks actuality. This is not merely a semantic distinction. It changes how experiments are designed and interpreted. If you set up an experiment to observe interference, you must allow the wave aspect to remain intact. If you try to track which path a photon takes, the interference disappears. The act of measurement itself determines which description becomes relevant. This is often summarized somewhat misleadingly by saying that light chooses to behave like a wave or a particle depending on how you look at it. That phrasing gives too much agency to light and too little to the experimental setup. Light does not choose. The rules governing probabilities and interactions simply play out within the constraints you impose. If you design an experiment that preserves information about multiple paths, the wave description applies. If you design one that forces a definite path, the particle description dominates. You cannot have both simultaneously in full form. This is not because light is hiding information out of spite. It is because the concepts of wave and particle are mutually exclusive ways of organizing information. They are not properties of light itself. They are properties of our descriptions. At first, this feels unsatisfying. It can sound like a retreat, as if science is admitting defeat. But in practice, it is the opposite. By letting go of the demand for a single classical picture, physicists gained a framework that worked consistently and predictively. This framework is quantum mechanics, and within it, light occupies a special but not unique role. Other entities like electrons also exhibit wave-particle duality. Light was simply the first place where the conflict became impossible to ignore. In quantum mechanics, the fundamental object is not a wave or a particle, but a quantum state. This state contains all the information that can be known about the system. It evolves according to strict rules, and from it, probabilities of different outcomes can be calculated. For light, the quantum state describes how the electromagnetic field is configured. It tells you the likelihood of detecting photons in various places, with various energies and properties. It does not tell you what will happen in a specific trial. It tells you what can happen and how likely each possibility is. When an interaction occurs, such as a photon being absorbed, one of those possibilities becomes real. The rest vanish from relevance. This transition from possibility to outcome is often called collapse, though that word brings its own complications. What matters here is that the wave description governs the build-up of possibilities, while the particle description governs the outcome. The compromise, then, is not a blend but a division of labour. Waves handle evolution. Particles handle events. This division helps explain why light sometimes seems ghostly and spread out, and sometimes sharply localized. Between interactions, light is not an object in space. It is a pattern of probabilities. At the moment of interaction, it produces an object-like effect. This also explains why asking what is light really often leads to frustration. The answer depends on what aspect you are focusing on. If you mean how light moves and spreads, it is best described by waves. If you mean how light exchanges energy with matter, it is best described by particles. If you insist on a single picture that covers both perfectly, you will be disappointed. The compromise becomes even stranger when you consider that the wave description does not live in ordinary space in the way classical waves do. It lives in an abstract mathematical space that encodes all possible configurations. This makes it harder to visualize, but also more powerful. In this sense, light is not made of waves or particles. It is made of quantum states that produce wave-like probabilities and particle-like events. That may sound like wordplay, but it reflects a genuine shift in how physical reality is described. What is particularly striking is how precise this framework is. Despite its abstract nature, it produces predictions that match experiments to extraordinary accuracy. The rules governing light's behavior have been tested again and again, and they hold. This precision suggests that the compromise is not a flaw or a temporary patch. It is a reflection of how nature actually works at small scales. Our discomfort arises not because the theory is sloppy, but because our intuition is tuned to a different domain. Light does not care whether we find its behavior aesthetically pleasing or conceptually tidy. It behaves according to rules that are consistent, even if they do not align with everyday expectations. As you sit with this, it may help to notice that similar compromises appear elsewhere in life. A map is not the territory, but it is useful. A musical score is not the sound, but it guides performance. A recipe is not the meal, but it produces one. Different descriptions serve different purposes. Wave and particle descriptions are like that. They are not competing claims about what light is made of. They are complementary ways of organizing information about how light behaves under different conditions. The word complementary is important here. It does not mean redundant. It means mutually necessary and mutually exclusive. You need both, but you cannot apply both fully at the same time. This idea takes some getting used to. It challenges the expectation that a complete description must be singular and unified at all levels. Instead, completeness emerges from knowing when to use which description. Light embodies this lesson vividly. It forces a kind of intellectual flexibility, a willingness to let go of rigid categories and accept that reality may not fit neatly into them. This flexibility does not mean anything goes. The rules are strict. The mathematics is unforgiving. Predictions are precise. What changes is not rigor, but interpretation. As this part settles into place, the strange compromise between wave and thing remains active, unresolved in the sense that it does not collapse into something simpler. It remains a feature, not a bug. When the word photon is used, it often sounds reassuringly concrete, as if it finally gives light a smallest piece, something definite you can point to and say, this is it. This is what light is made of. A photon sounds like a tiny object, a grain, a bead of brightness moving through space. That image is understandable, but it quietly smuggles in assumptions that do not quite hold. Photons are messengers, yes, but they are not messengers in the way envelopes or packages are. They do not carry a note written on paper. They are the note, the delivery, and the act of delivery all at once. To understand why photons are described this way, it helps to return to the idea of light as interaction rather than substance. A photon does not exist as a thing sitting somewhere waiting to be picked up. It exists as a transfer. Energy leaves one place and appears in another, and the photon is the name we give to that indivisible transaction. Without an emission and without an absorption, the concept of a photon loses its meaning. This is one of the reasons photons feel so elusive. Most objects can be described independently of what they do. A rock is still a rock even if nothing touches it. A chair remains a chair whether or not someone sits in it. A photon, by contrast, is defined by what happens. It is born in an interaction and ends in an interaction. In between, it is described not as a location, but as a set of possibilities. When an atom emits light, it does so because one of its electrons changes energy levels. Electrons in atoms are not free to take on any energy they like. They occupy specific allowed states, like rungs on a ladder. When an electron drops from a higher rung to a lower one, the energy difference has to go somewhere. That energy is released as a photon. The photon's energy is exactly equal to the difference between those two states. It cannot be adjusted. It cannot be shaved down or stretched out. This precision is one of the defining features of photons. They are not vague carriers of some energy. They carry a specific amount determined by frequency. That frequency also determines the photon's character in other ways. Higher frequency photons carry more energy. Lower frequency photons carry less. This is why different kinds of light have different effects. A photon in the visible range might trigger a response in your eye. A lower frequency photon might contribute to warmth. A much higher frequency photon can break chemical bonds or damage cells. Despite these differences, all photons share some remarkable properties. They all move at the same speed in a vacuum. They all have zero rest mass. They all carry momentum even though they have no mass in the usual sense, and none of them can exist at rest. This last point is particularly important. You cannot stop a photon and examine it. You cannot put it on a scale. You cannot hold it still. The moment a photon stops moving, it stops being a photon. It has been absorbed. This makes photons fundamentally different from particles of matter. Matter can accumulate. Photons cannot. Matter can sit quietly. Photons cannot. Matter persists through time. Photons, in a sense, do not experience time at all. According to relativity, time passes more slowly for objects that move faster. As an object's speed approaches the speed of light, time dilation becomes extreme. For something moving exactly at the speed of light, time does not pass. From the photon's perspective, if such a perspective can even be meaningfully defined, emission and absorption are the same instant. This idea is difficult to wrap your mind around, but it reinforces the idea of photons as connectors rather than travelers. They link events across space-time without themselves undergoing a journey. When a star emits light that eventually reaches your eyes, it feels natural to imagine that light travelling for years or centuries, and from your perspective, it does. But for the photon, there is no waiting. There is no aging. There is no in-between. There is only the connection. This is part of why photons are often described as messengers. They carry information about where they came from. The energy they carry tells you something about the processes that produced them. Their direction tells you where that source is. Their polarization can tell you about magnetic fields they encountered along the way. Their arrival time can tell you about distance and motion. Light allows the universe to communicate with itself. Without photons, distant events would be isolated. Stars would burn unseen. Galaxies would evolve in silence. Even within your own body, photons play a role, triggering chemical changes in the retina that allow vision to happen at all. But these messages are not written in words, they are written in structure. A photon's properties encode information, and that information is decoded through interaction. What makes this even stranger is that photons do not carry information in the way a package carries a message. There is no little tag attached to a photon saying where it came from or what it means. The information is implicit in its energy, momentum, and quantum state. This is why light can be analysed to learn about things unimaginably far away. By splitting light into its component frequencies, scientists can determine the chemical composition of stars. Specific atoms absorb and emit photons at specific energies. Those patterns act like fingerprints. All of that information arrives without anything material making the journey. No piece of the star travels to Earth. Only photons do, and they are not pieces of the star in any ordinary sense. They are the result of interactions that happened there long ago. This again brings us back to the idea that photons are not objects in the traditional sense. They are records of change. Each photon is evidence that something happened somewhere. This perspective also helps explain why photons are the smallest messengers, not in terms of size, but in terms of indivisibility. You cannot have half a photon. You cannot detect a fraction of one. Interactions occur one photon at a time. Even when light seems continuous, like the steady glow of a lamp, it is actually composed of an enormous number of individual photons arriving in rapid succession. The continuity is an illusion created by scale. At human time scales, the discreteness is hidden. At smaller scales, it becomes visible. Sensitive detectors register individual photons as distinct events. The randomness of their arrival times becomes apparent. Patterns emerge only when many events are collected. This randomness is not a flaw or a lack of control. It is a fundamental feature. Photons are emitted and absorbed probabilistically. You can predict averages with extreme accuracy, but you cannot predict exactly when a specific photon will arrive. This probabilistic nature is often uncomfortable. It feels like uncertainty, where certainty should exist. But it is important to recognize that the uncertainty does not lie in the laws. It lies in the outcomes of individual events. The rules governing the probabilities are precise. Photons also exhibit properties that further challenge classical intuition, such as polarization and entanglement. Polarization describes the orientation of the electromagnetic oscillations associated with the photon. This orientation affects how photons interact with materials, whether they pass through certain filters, and how they reflect. Entanglement, on the other hand, describes a situation where two or more photons are linked in such a way that their properties cannot be described independently. Measure one, and you instantly gain information about the other, no matter how far apart they are. This does not mean information is travelling faster than light. It means that the quantum state describing the system is shared. The photons are not separate messengers. They are parts of a single description. This further erodes the idea of photons as independent little particles. They can be correlated in ways that defy classical separation. They can behave as aspects of a larger whole. Even the act of detecting a photon is more complex than it sounds. Detection is not simply a matter of a photon hitting something. It is a quantum interaction that results in a measurable change, such as an electron being excited or a current being produced. Until that interaction happens, the photon is not localized. It is not at a specific point. It exists as a set of probabilities. Detection forces a specific outcome, but it does not reveal a hidden path the photon took. It creates the event. This means that photons are not tiny objects traveling along invisible tracks. They are processes unfolding according to rules that link possibility and actuality. The language of messengers is useful because it emphasizes connection. A photon connects a change in one place to a change in another. It does not linger. It does not leave behind a trail. It simply makes the connection and vanishes. This view also helps explain why photons play such a central role in physics. They mediate electromagnetic interactions. They allow charged particles to influence each other across distance. They are responsible for forces, radiation, and the structure of atoms. In quantum field theory, light is described not as a collection of photons, but as an electromagnetic field that can exchange energy in discrete units. Photons are the excitations of that field. They are the moments when energy moves from the field to matter or vice versa. This framing again shifts the focus away from objects and toward interactions. The field exists everywhere. Photons are events within that field. Thinking this way requires patience. It resists visualization. It does not offer a simple picture you can hold on to, but it does offer consistency. Every experiment fits. Every prediction holds. As you listen to this, photons are arriving from the screen, from the room, from distant lights outside. Each one triggers tiny changes in your eyes. None of them announces itself. None of them leaves a mark. And yet together they build the experience you are having right now. That experience feels continuous, stable, and solid. Beneath it is a constant stream of indivisible events, happening too quickly and too quietly to notice individually. The smallest messengers do not shout. They whisper in numbers large enough to matter. What makes photons especially interesting is that they are both fundamental and limited. They are fundamental in the sense that they cannot be broken down into smaller carriers of light. They are limited in the sense that they only exist as long as the interaction they represent remains incomplete. Once a photon is absorbed, it is gone. The energy it carried has been transferred. The message has been delivered. There is nothing left to examine. This ephemerality is not a weakness. It is part of what allows light to be such an effective messenger. Photons do not clutter the universe. They do not pile up. They appear when needed and disappear when their job is done. This makes light remarkably efficient. Energy and information move without leaving debris. The universe remains clean, in a sense, even as it communicates endlessly. Colour feels immediate. You do not calculate it. You do not reason your way into it. You open your eyes, and it is simply there, spread across the world in countless variations. Blue sky, green leaves, warm amber light at dusk. The experience is so seamless that it is easy to forget how many steps are involved, how much interpretation is happening, and how little of it actually belongs to light itself. Because colour is not something light possesses on its own. It is something that happens between light and you. This is where the idea of colour as a conversation becomes useful. Light speaks in energy. Your eyes listen in biology. Your brain translates. What you experience as colour is the result of that exchange, not a property carried intact from source to surface to sight. To see why this matters, it helps to begin with what light brings to the interaction. Photons arrive with a specific energy. That energy is tied directly to frequency. Higher frequency photons carry more energy. Lower frequency photons carry less. This range of energies spans far beyond what you can see, from radio waves at the low end to gamma rays at the high end. Your visual experience occupies only a narrow slice of that vast spectrum. Within that slice, different energies correspond to what we label as different colours. But those labels are conveniences, not fundamental divisions. There is no sharp boundary where red suddenly becomes orange or green becomes blue. The spectrum is continuous. Colour names are categories imposed by perception and language. When light reaches your eye, it does not arrive as red or blue. It arrives as photons with particular energies. The eye's job is not to recognise colour directly, but to respond differently to different energies. Inside your retina are specialised cells called photoreceptors. There are two main types involved in vision: rods and cones. Rods are highly sensitive to light and allow you to see in low light conditions, but they do not distinguish colour. Cones are less sensitive but come in different varieties, each tuned to respond most strongly to a particular range of photon energies. Most humans have three types of cones. One type responds best to higher energy visible photons, another to medium energies, and another to lower energies. These are often loosely referred to as blue, green, and red cones, but that shorthand can be misleading. Each type responds across a range, not a single point. When photons enter your eye, they interact with molecules inside these cone cells. That interaction triggers a cascade of chemical changes, ultimately producing electrical signals. Different cones respond with different strengths depending on the energy of the incoming photons. Your brain does not receive a label saying this photon was green. It receives a pattern of activity, how strongly each type of cone responded. Colour emerges from the comparison of these responses. This is why colour is a conversation. Light provides the input. Your eye responds selectively. Your brain interprets the pattern. If two different light sources produce the same pattern of cone responses, they will look the same colour to you, even if their actual photon distributions are different. This is not a hypothetical scenario. It happens all the time with artificial lighting. Two lights with very different spectral compositions can appear identical in colour, because they stimulate your cones in the same way. This means that colour is not an absolute property of light. It is relational. It depends on the observer. Different species experience colour differently, because their eyes have different sets of photoreceptors. Some animals see fewer colours than humans. Others see more. Birds, for example, often have additional cone types that allow them to see ultraviolet light. What looks like a uniform surface to you may be richly patterned to them. Even among humans, colour perception varies. Some people have cones that are missing or altered, leading to different experiences of colour. Others have subtle shifts in sensitivity that change how colours appear without ever being noticed. This variability reinforces the idea that colour does not live in the world by itself. It lives in the interaction. Still, light plays an essential role. Without differences in photon energy, there would be nothing for the eye to compare. The conversation requires both participants. The story becomes even more interesting when you consider how objects acquire their colours. A red apple does not contain redness as a substance. It contains molecules arranged in such a way that they absorb certain photon energies and reflect others. When white light, which contains a broad range of visible photon energies, strikes the apple, some photons are absorbed. Their energy is transferred into molecular vibrations or electronic changes. Other photons are reflected. Those reflected photons are what reach your eye. The apple appears red because it reflects photons in the lower energy visible range more efficiently than others. But that redness exists only when there is light to reflect and an eye to receive it. In darkness, the apple has no colour. Under different lighting, its colour can shift. This dependence on context is another sign that colour is not a fixed property. Change the light source, and colours change. Sunlight, candlelight, and LED light all have different spectral compositions. They stimulate your cones differently, altering the conversation. Your brain works constantly to compensate for these changes. This process, called colour constancy, allows you to perceive objects as having relatively stable colours, even under different lighting conditions. A white shirt looks white at noon and at sunset, despite the very different light illuminating it. This compensation is not perfect. Under unusual lighting, colours can look distorted, but most of the time your brain quietly adjusts, maintaining a sense of continuity. That adjustment further distances colour from being a simple property of light. It is an interpretation layered on top of sensory input, informed by experience and expectation. Yet, despite all this complexity, colour feels immediate and effortless. You do not consciously calculate cone responses or spectral distributions. The conversation happens below awareness, producing a smooth result. This smoothness can make it tempting to think of colour as something that light carries intact, like paint on a brush. But the reality is more dynamic. Light offers energy differences. The eye samples them. The brain constructs an experience. This construction process becomes especially clear in cases where colour appears without a corresponding external stimulus. After images, for example, occur when cones become temporarily less responsive after prolonged stimulation. Look at a bright red object for a while, then look away, and you may see a greenish afterimage. The light is not green. The pattern of cone activity is. Similarly, certain optical illusions create colours that are not present in the stimulus at all. The brain fills in information based on context, edges, and expectations. These effects are not bugs. They are features of a system optimized for usefulness rather than accuracy. Colour helps you distinguish objects, assess ripeness, detect changes, and navigate environments. It does not need to be a perfect map of photon energies to be effective. From the perspective of light, none of this matters. Light does not care how it is perceived. It delivers energy according to physical laws and continues on its way or vanishes upon absorption. From the perspective of perception, however, light becomes meaning. It becomes surface, depth, contrast, and emotion. Certain colours feel warm, others feel cool, some feel calming, others feel stimulating. These associations are partly cultural and partly biological. They arise from repeated interactions between light, environment, and experience. Even language reflects this. We speak of bright moods, dark thoughts, warm tones, cold light. These metaphors grow out of how colour and light influence feeling, not just vision. At this point, it becomes clear that asking what colour is made of is as slippery as asking what light is made of. Colour is not made of photons in the same way light is not made of particles. Colour is made of interaction. This does not make it any less real. Experiences are real even when they are constructed. Pain is real. Sound is real. Colour is real. Their reality lies in experience, not in material composition. What makes colour especially interesting in the context of light is how efficiently a small range of physical differences produces such a rich variety of experiences. Tiny differences in photon energy lead to dramatic differences in perception. This sensitivity allows humans to distinguish millions of colours, even though the underlying physical range is narrow. The brain amplifies differences, enhancing contrast and creating boundaries. That amplification can sometimes mislead. Colours can appear different depending on surrounding colours. A grey square can look warm or cool depending on its context. The light itself has not changed. The interpretation has. These effects highlight the conversational nature of colour. The eye does not passively receive information, it actively interprets it. Light, in this sense, is offering possibilities. The eye selects, the brain negotiates. When thinking about what light is made of, colour serves as a reminder that composition alone does not determine experience. The same photons can produce different colours depending on context. The same light can feel harsh or gentle depending on timing, intensity and expectation. This brings us back to the idea of photons as messengers. A messenger does not control how the message is understood. It delivers content. Interpretation happens elsewhere. Photons deliver energy and structure. Colour is the interpretation that follows. As you listen, light continues to arrive at your eyes, triggering countless microscopic interactions. Each one contributes to a seamless visual field that feels stable and obvious. Beneath that stability is constant negotiation. The world you see is not a direct imprint of light on your mind. It is a translation. That translation is usually so reliable that it fades into the background. But when you slow down and consider it, the process becomes quietly remarkable. Something as abstract as electromagnetic energy becomes something as immediate as colour. This transformation does not require awareness. It happens whether you think about it or not. But thinking about it can change how you experience light, even subtly. Colours may begin to feel less like surfaces and more like signals, less like properties and more like conversations that renew themselves moment by moment. Even when you close your eyes, light does not stop. The room may fade from awareness, colours may dissolve into darkness, but light continues to move, to interact, to pass through walls, through air, through your body itself. Most of it never reaches awareness, not because it is absent, but because your senses are selective. What you see is only a thin slice of what is happening. This is where the idea of invisible light becomes important, because it reveals how limited ordinary perception really is. The light you can see, the narrow band of energies that produce colour and brightness, is only a small fraction of what exists. Beyond that thin window stretches an enormous range of electromagnetic activity, filling space constantly, quietly, without announcement. To understand this, it helps to return to the idea of light as electromagnetic radiation. What distinguishes one kind of light from another is not substance, not material composition, but energy, frequency, wavelength. These are different ways of describing the same thing: how rapidly the electromagnetic fields oscillate, how much energy each photon carries. Visible light occupies a modest middle ground. Below it in energy are radio waves, microwaves, and infrared radiation. Above it are ultraviolet light, X-rays, and gamma rays. All of these are forms of light. All of them are made of the same kind of messenger, photons. The only difference is how energetic those photons are. This alone can feel counterintuitive. Radio waves and gamma rays feel nothing alike. One carries music into a car, the other is associated with cosmic violence and nuclear reactions, and yet, at the most fundamental level, they differ only by scale, by how tightly their waves are packed, by how much energy each photon delivers. This continuity is one of the most elegant aspects of light. There are no sharp boundaries in nature separating radio from infrared, or visible from ultraviolet. Those categories are conveniences created to help humans talk about effects. The electromagnetic spectrum is a smooth gradient. Most of that gradient is invisible to you, but invisible does not mean inactive. Radio waves, for example, pass through you constantly. Signals from broadcast towers, satellites, Wi-Fi routers, and distant astronomical sources move through your body without resistance. They interact weakly with your tissues, carrying information rather than heat or damage. Microwaves occupy a higher energy range. They are still invisible, but they interact more strongly with matter. They can cause molecules, especially water molecules, to rotate and vibrate. This is why microwave ovens work. They excite molecular motion, producing heat. Infrared radiation sits just below visible red light. You cannot see it, but you can feel it as warmth. Every warm object emits infrared light. Your body does. The walls around you do. The Earth itself radiates infrared energy into space. Infrared cameras do not see heat directly. They detect infrared photons and translate them into visible colors. They make the invisible visible by converting one part of the spectrum into another. Above visible light lies ultraviolet. Ultraviolet photons carry more energy than visible ones. They can trigger chemical reactions. They can damage DNA. They can also drive important biological processes such as vitamin D production in skin. X-rays and gamma rays carry even more energy. They penetrate deeply into matter. They pass through soft tissues. They interact strongly with dense materials. They reveal bones. They reveal cosmic events. They reveal processes that cannot be observed in any other way. All of these forms of light are present in the environment to varying degrees. Some are produced naturally. Some are produced artificially. Some arrive from deep space, having travelled for millions or billions of years before passing quietly through you. Most of the time, you are unaware of this constant passage. Your senses are tuned for survival, not completeness. You see what helps you navigate, find food, recognise faces, and avoid danger. The rest is filtered out. This filtering can give the impression that invisible light is somehow separate from visible light, as if it belongs to a different category altogether. But physically, there is no such separation. The same rules apply. The same fields oscillate. The same photons carry energy. The difference lies in interaction. Visible light interacts strongly with the molecules in your retina. Infrared interacts more with thermal motion. Radio waves interact with electrical circuits. X-rays interact with dense matter. Interaction determines relevance. This idea becomes especially clear when you consider that invisible light can be detected and used in ways that extend human perception far beyond its natural limits. Radios convert radio waves into sound. Thermal cameras convert infrared into images. X-ray detectors convert high-energy photons into diagnostic information. In each case, a device acts as an interpreter, standing in for a biological sense that does not exist. The device engages in the conversation instead of your eye, translating the message into a form you can understand. This reinforces the idea that light itself is neutral. It does not come labelled as visible or invisible. Those labels reflect the limits of perception, not the structure of reality. It also reveals how much of the universe operates beyond direct experience. Entire processes unfold in ranges of light you never see. Star formation hidden by dust becomes visible in infrared. Explosive cosmic events reveal themselves in gamma rays. Cold clouds of gas announce their presence through radio emissions. Without invisible light, much of modern science would simply not exist. The universe would appear quieter, simpler, and far less dynamic than it truly is. Even on Earth, invisible light plays a constant role. Infrared radiation governs heat transfer. Ultraviolet light influences weather patterns, ecosystems, and biological rhythms. Radio waves enable communication across continents. These influences do not announce themselves. They blend into the background, shaping conditions rather than demanding attention. This subtlety is part of why invisible light can feel abstract. You cannot point to it directly. You cannot see it without assistance, but its effects are everywhere. Your body absorbs infrared radiation from its surroundings and emits its own. This exchange contributes to thermal balance. The warmth you feel from a nearby person or object is not air alone. It is infrared light travelling between surfaces. At night, when visible light fades, infrared continues unabated. The world does not go quiet. It simply shifts into a different register. This constant presence challenges the idea that darkness is the absence of light. Darkness is the absence of visible light. Invisible light remains. Even deep space, often described as empty and cold, is filled with electromagnetic radiation. A faint background glow permeates the universe, the remnant of its early history. Photons from that time still move through space, stretched and cooled by cosmic expansion, now existing in the microwave range. These ancient photons are invisible to your eyes, but they are real, measurable, and informative. They carry information about the universe when it was young, long before stars or planets existed. This means that light is not only around you in space, it is around you in time. Photons from different eras overlap in the present, arriving together from vastly different origins. Some photons reaching you now left their sources moments ago, others left millions of years ago, others have been travelling since near the beginning of everything. All coexist in the same moment. This layering of histories is easy to miss because perception collapses it into a single experience. The world looks stable, continuous, present. But beneath that stability is a constant flow of messages from different times and places, most of them invisible. The fact that light can be invisible and yet active also helps clarify what light is made of. If light were a substance, invisibility might imply absence. But light is not substance. It is energy structured in specific ways. That energy does not care whether it is seen. It does not require observation to exist or propagate. It moves according to physical laws regardless of attention. This is important when considering ideas about observation and reality. Light does not wait to be noticed. It does not require an eye to complete its journey. Observation affects how light is measured, not whether it exists. Invisible light demonstrates this clearly. It fills space whether or not there is a detector. Its presence can be inferred through effects even when it is not directly measured. For example, the warmth of sunlight on your skin includes a significant infrared component. You feel it even if your eyes are closed. The energy transfer happens independently of vision. Similarly, ultraviolet light can cause sunburn even when it does not feel bright. The damage occurs regardless of awareness. These examples underline a simple point. Light interacts whether or not it is perceived. This interaction-based understanding helps resolve confusion about why different kinds of light matter. It is not about visibility. It is about how energy couples to matter. Visible light couples efficiently to the photoreceptors in your eyes. Infrared couples efficiently to molecular motion. Radio waves couple efficiently to oscillating charges in antennas. X-rays couple efficiently to dense atomic structures. Each range finds its partner. In that sense, invisible light is not hidden. It is simply speaking to different listeners. Your eyes are one listener among many. As you sit quietly now, surrounded by unseen radiation, nothing dramatic is happening. There is no danger implied. Most of the light passing through you is gentle, low energy, harmless. It has always been there. Your body evolved within it. The point is not to provoke concern, but to expand perspective. The world is richer, more layered, and more active than direct experience suggests. Light is not just what you see. It is what structures environments, regulates systems, and connects distant events. Visibility is a local detail. Invisible light remains present, not as a separate category, but as a reminder that the universe operates across scales and ranges far beyond immediate perception. Once light is understood as something that moves, carries energy, and connects events, it becomes impossible to ignore the way it interacts with the very ideas of time and space. Not as background concepts, not as abstract containers where things happen, but as participants. Light does not simply travel through time and space as they already exist. It helps define what time and space mean in the first place. This realization did not arrive all at once. It emerged slowly from small inconsistencies and uncomfortable observations, from experiments that refused to behave as expected. At first, time and space were treated as stable stages. Things happened within them, but they themselves remained unchanged. Light moved across space. Events happened in time. Everything seemed neatly separated, but light did not cooperate with that separation. One of the first clues came from something deceptively simple. No matter how fast the source of light moved, and no matter how fast the observer moved, the measured speed of light remained the same. This was not just surprising, it was deeply unsettling. Every other kind of motion behaved differently. If you ran toward a sound, you encountered the sound waves sooner. If you chased them, they seemed slower. Light did not behave that way. This stubborn consistency forced a choice. Either the measurements were wrong, or the assumptions about time and space were incomplete. The measurements were repeated, refined, and confirmed. The assumptions had to give way. What emerged was a new understanding. Time and space were not independent, absolute entities ticking along in the background. They were intertwined, flexible, and influenced by motion and gravity. Light sat at the center of this realization, not because it caused the changes, but because its behavior revealed them. The speed of light became more than just a number. It became a structural limit. Nothing carrying information or energy could exceed it. This was not a technical constraint. It was woven into how cause and effect operate. Light set the pace at which the universe could communicate with itself. This immediately linked light to time. If there was a maximum speed at which information could travel, then simultaneity could no longer be universal. Two events that appeared to happen at the same time to one observer might not appear simultaneous to another observer moving differently. There was no single global now. Light exposed this quietly but decisively. Because signals could not travel faster than light, different observers could not agree on the timing of distant events without accounting for their own motion. Time became relative, not subjective in the everyday sense, but dependent on physical circumstances. This dependence is subtle in daily life. At human speeds and distances, the effects are tiny. Clocks tick almost in unison. Lengths appear stable. Time feels shared. But the structure underneath is different from what intuition suggests. Light forces time to behave differently for different observers, move faster, and time slows down relative to someone at rest. This is not a psychological effect, it is physical. Clocks carried on fast-moving objects tick more slowly than identical clocks left behind. This has been measured directly. Light is involved because it defines the framework within which motion is measured. The rules governing light's speed require time to adjust so that the speed remains constant for all observers. Space adjusts as well. Lengths contract in the direction of motion. Time and space bend just enough to keep light consistent. This adjustment is not something light does actively. It is not pushing or pulling on time. Rather, the laws that govern light reveal that time and space are not rigid. They respond. This response becomes even more pronounced when gravity enters the picture. Massive objects do not just attract other objects, they affect the flow of time and the structure of space. Light moving near a massive object follows curved paths. Its frequency shifts, its timing changes. This means that light does not simply pass through gravitational fields unchanged. It responds to them, and in doing so, it carries information about them. When light climbs out of a strong gravitational field, it loses energy. Its frequency decreases. This effect, known as gravitational redshift, has been observed and measured. It tells us that gravity affects time itself. Clocks deeper in a gravitational field tick more slowly than clocks farther away. Again, light is central. Because light carries energy and frequency, changes in its properties reveal changes in time. Light becomes a probe of temporal structure. This leads to a remarkable conclusion. Time does not flow at the same rate everywhere. It depends on motion and gravity. Light does not cause this variability, but it makes it visible. Space, too, reveals its flexibility through light. When light passes near massive objects, its path bends. This bending has been observed in eclipses, where starlight passing near the sun appears displaced. Space itself is curved, and light follows those curves. This curvature is not a force acting on light in the usual sense. Light always travels in the straightest possible path within the geometry of space-time. If space is curved, the straightest path is curved too. This idea challenges the notion of straight lines as absolute. What looks straight depends on the structure of space. Light traces that structure faithfully. Because of this, light becomes a kind of ruler and clock combined. By observing how light travels, bends, and changes frequency, scientists can infer the shape of space-time. This is not a metaphor, it is a practical method. Entire fields of astronomy and physics rely on light to map gravity, measure distances, and track the expansion of the universe. For example, the expansion of the universe itself is observed through light. As space expands, the light travelling through it stretches, its wavelength increases, its frequency decreases. Distant galaxies appear redshifted not because they are moving through space like debris in an explosion, but because space itself is stretching between us and them. Light carries that stretching in its structure. By measuring the shift, we learn about the history and rate of expansion. Here again, light is not passive. It does not merely reflect what is already known. It encodes changes in space-time within its own properties. This encoding happens automatically. Light does not need to be aware of gravity or expansion. It simply obeys the rules, and those rules tie its behavior to the geometry of the universe. At this point, the phrase, light touches time and space, becomes more literal than poetic. Light interacts with the deepest structures that define reality. It is sensitive to motion, mass, and geometry. This sensitivity has practical consequences even close to home. Technologies like GPS rely on precise timing. Satellites orbiting Earth experience different gravitational conditions and speeds than receivers on the ground. Their clocks tick at different rates. Light signals exchanged between satellites and receivers must account for these differences. Without corrections based on relativity, GPS systems would drift rapidly, producing errors of kilometers. This means that everyday navigation depends on light's relationship with time and space. What seems abstract is quietly operational. Light also defines causal structure. Because nothing can travel faster than light, there is a limit to what can influence what. Events outside each other's light cones cannot affect one another. This structure shapes what kinds of interactions are possible. The idea of a light cone is a way of visualizing how light links events in space-time. From any event, light can travel outward, defining a region of influence. Inside that region, cause and effect are possible. Outside it, they are not. This structure gives time direction and order. It ensures that causes precede effects. Light enforces this not by choice, but by being the fastest messenger. Without light's finite speed, causality would lose its structure. Everything could influence everything else instantly. The universe would behave very differently. Light's role here is not optional. It is foundational. Even at the quantum level, where time becomes more ambiguous, light remains a reference. Quantum interactions propagate at or below the speed of light. Entanglement correlations may appear instantaneous, but they do not allow information to travel faster than light. Causality remains intact. This consistency across scales reinforces the idea that light is woven into the framework of reality, not layered on top of it. When asking what light is made of, this becomes relevant in a subtle way. Light is not just something within space-time, it is part of how space-time reveals itself. Photons carry energy and momentum, but they also trace the geometry of the universe. They follow its curves, they respond to its stretching, they reveal its structure. This dual role makes light unique. It is both actor and witness. Time, as experienced by humans, feels like a steady flow. But light reveals that flow to be variable. It stretches and compresses depending on conditions. Space feels solid and fixed. Light reveals it to be dynamic and responsive. These revelations do not invalidate everyday experience. They sit beneath it. At human scales, the effects are small enough to be ignored, but they are always present. As you sit now, light from the room reaches your eyes. That journey took time, even if the delay is too small to notice. Gravity shaped that journey, even if the curvature is negligible. Motion matters, even if relative speeds are low. Everything that makes this moment possible depends on light interacting with time and space in consistent ways. This interaction does not demand attention. It happens quietly, continuously, without drama, but it reshapes how reality is understood. Light does not merely exist in time, it helps define it. Light does not merely occupy space, it reveals its shape. This makes light less like a substance and more like a structural element, a thread that stitches together events, distances, and durations. When light is spoken of as energy, the word can feel vague, almost interchangeable with usefulness or power. We talk about having energy, lacking energy, conserving energy, without always stopping to ask what the word actually means in a physical sense. In physics, energy is not a feeling or a resource you carry around. It is a way of accounting for change. It is the bookkeeping system that keeps track of what can happen and what cannot. Light fits into this system in a very particular way. It is energy in transit, energy that does not sit still, energy that refuses to be stored in place without immediately becoming something else. And because energy is tied so closely to how reality behaves, light ends up playing a quiet but central role in shaping what the universe can do. One of the most striking things about light is that it carries energy without carrying mass, at least not rest mass. Photons have energy and momentum, but they do not weigh anything in the way matter does when it is at rest. This alone makes light unusual. Most things that carry energy are also made of matter. A moving object carries kinetic energy. A compressed spring carries potential energy. A hot object carries thermal energy. In each case, the energy is tied to something that can be weighed, held, or pointed to. Light breaks that pattern. It carries energy directly, without needing a material container. When sunlight warms your skin, energy has been transferred, but no matter has arrived. When a plant uses light to power photosynthesis, energy enters the system without adding mass. When a solar panel generates electricity, energy flows from light into electrons without anything tangible being delivered. This ability to move energy without moving matter is one of the reasons light is so influential. It allows change to propagate across vast distances efficiently. Stars can affect planets across empty space. Galaxies can influence each other's evolution through radiation. Information and energy can travel without dragging material along behind them. Energy conservation plays a key role here. Energy cannot be created or destroyed, only transformed. When light is emitted, energy leaves one system and enters another. When light is absorbed, its energy becomes something else. Heat, chemical change, motion, electrical current. Light is not exempt from this accounting. Every photon's energy must be accounted for. If light warms something, that warmth comes from the light's energy. If light knocks an electron loose, that energy comes from the photon. Nothing appears from nowhere. This strict bookkeeping gives light a kind of honesty. It cannot cheat. It cannot deliver more energy than it carries. It cannot disappear without consequence. Because photons carry energy proportional to their frequency, light links energy directly to time. Frequency is a measure of how rapidly something oscillates. Higher frequency means more oscillations per second. More oscillations per second means more energy per photon. This connection between energy and frequency is not arbitrary. It reflects a deep relationship between time and change. Faster oscillations correspond to higher energy, because more change is happening in less time. This is one of the places where light reveals the shape of reality rather than just occupying it. The rules connecting energy, frequency, and time are not optional. They are structural. They define what interactions are possible. For example, certain chemical reactions require photons above a specific energy threshold. Below that threshold, nothing happens. No amount of waiting will help. The interaction is forbidden. Above the threshold, it proceeds. This threshold behavior shapes everything from vision to chemistry to biology. It determines which wavelengths of light drive photosynthesis, which damage DNA, which trigger vision, and which pass through harmlessly. These thresholds are not negotiated. They are consequences of how energy levels are structured in atoms and molecules. Light must meet the requirement or be ignored. In this way, light acts as a gatekeeper. It allows certain changes and forbids others. The shape of reality, at the microscopic level, is defined by which energy exchanges are allowed. Light also connects energy to momentum. Even though photons have no rest mass, they carry momentum. When light strikes an object, it exerts pressure. This pressure is tiny in everyday situations, but it is real and measurable. Solar sails take advantage of this. By reflecting light, they gain momentum from photons. Over time, this momentum accumulates, producing motion without fuel. The energy and momentum carried by light-shaped trajectories. This again challenges intuition. How can something without mass push something with mass? The answer lies in the way energy and momentum are related. In relativity, energy itself has inertia. Anything that carries energy resists changes in motion. Light carries energy, therefore it carries momentum. This blurs the line between matter and radiation. Matter and light are not separate categories. They're different manifestations of energy under different conditions. This becomes even clearer when considering the relationship between energy and mass. According to relativity, mass itself is a form of energy. The famous equation connecting mass and energy is not a slogan. It is a statement that mass and energy are interchangeable under the right circumstances. Light makes this interchangeability explicit. In certain interactions, light can produce matter. High-energy photons can transform into particle-antiparticle pairs when conditions allow. Conversely, matter can annihilate into light, converting mass directly into radiant energy. This is not theoretical speculation. It has been observed and measured. In these processes, light and matter are not opposites. They are expressions of the same underlying currency. This means that light is not just energy moving through space. It is part of the fabric of what matter is allowed to become. The shape of reality, in this sense, is defined by transformation rules. Which forms of energy can turn into which others, which processes are permitted, which are forbidden. Light sits at the crossroads of many of these transformations. It is produced by changes in matter. It causes changes in matter. It mediates forces. It reveals structure. Because light moves at a fixed speed, energy carried by light has a built-in relationship to space and time. You cannot compress light energy into a smaller duration without increasing its frequency. You cannot spread it out without lowering its energy density. This constraint shapes what signals can look like, how quickly information can be transmitted, and how interactions unfold. It limits how sharply events can be localized in time and space. These limits are not inconveniences. They are stabilizing features. Without them, reality would behave very differently. Cause and effect would blur, structures would be unstable, the universe would not resemble the one we inhabit. Light also plays a central role in defining temperature. Temperature is a measure of average energy per degree of freedom in a system. Objects at higher temperatures emit more energetic radiation. As temperature increases, the spectrum of emitted light shifts toward higher frequencies. This relationship allows temperature to be measured remotely. By analysing the light emitted by an object, its temperature can be inferred. This works for stars, planets, and even distant galaxies. Here again, light acts as a translator. It turns internal energy into something that can be measured across distance. The universe cools as it expands, and light carries the record of that cooling. The faint background radiation filling space today is a snapshot of an earlier, hotter universe. Its energy distribution encodes information about the shape and history of reality itself. This means that light does not just respond to the shape of reality, it preserves it. It carries imprints of past conditions forward in time. Even within smaller systems, light shapes structure. Atoms are held together by electromagnetic interactions. Light mediates these interactions. Chemical bonds form and break through energy exchanges involving photons. Molecular shapes depend on energy landscapes shaped by electromagnetic forces. Without light, chemistry would not exist as it does. Without light, matter would behave differently. Structures would not form the same way. Life would not arise. This does not mean light causes everything. It means light participates in everything that involves electromagnetic interaction, which is most of what matters at human scales. Gravity shapes large-scale structure. The strong force shapes atomic nuclei. The weak force governs certain types of decay, but electromagnetism, carried by photons, governs structure, chemistry, and biology. This centrality makes light feel fundamental, but not in the sense of being the smallest building block. It is fundamental because it mediates relationships. When asking what light is made of, the question shifts again. Light is not made of pieces in the way matter is. It is made of energy organized according to rules that tie together space, time, and interaction. Those rules give reality its shape. They define what kinds of patterns can exist, how long they can persist, and how they can change. Light does not sit outside this structure. It is one of the threads that hold it together. As you rest with this idea, it may become easier to see why light keeps reappearing in so many contexts. Vision, heat, communication, astronomy, technology, fundamental physics. Light is present not because it is convenient, but because it is unavoidable. Energy must move. Information must propagate. Forces must act across distance. Light is how much of that happens. This does not mean light is the ultimate substance of reality. It means reality uses light as one of its primary tools. The shape of reality emerges from constraints, speeds that cannot be exceeded, energies that must be quantized, interactions that occur in steps. Light embodies these constraints. The relationship between light and reality remains open-ended. The deeper you look, the less light resembles a thing and the more it resembles a rule set made visible. There is a quiet temptation, once you realize how much light reveals, to assume that it can reveal everything. After all, light shows us distant galaxies, the structure of atoms, the curvature of space, the temperature of stars, the composition of atmospheres, and the movement of time itself. It crosses emptiness, survives vast distances, and arrives carrying information with remarkable fidelity. It feels natural to treat light as the ultimate messenger, capable of telling us anything we care to ask. But light has limits, and those limits matter just as much as its power. Not because light fails or behaves badly, but because information itself has boundaries. Light does not lie, but it also does not speak freely. It only tells what its interactions allow it to tell. Everything else remains silent. One of the first limits becomes clear when you consider that light only reports on what it interacts with. If something does not emit light, reflect light, absorb light, or alter light in some measurable way, then light has nothing to say about it. Entire regions of the universe can remain invisible, simply because they do not engage with electromagnetic radiation. This is not a failure of instruments or sensitivity, it is a fundamental limitation. Light cannot carry information about what does not touch it. Dark matter is a clear example. It does not emit light. It does not absorb light. It does not reflect light. As far as electromagnetic interaction is concerned, it may as well not exist, and yet its gravitational influence is unmistakable. Galaxies rotate too fast. Light bends around unseen mass. Large-scale structures form in ways that cannot be explained by visible matter alone. Light reveals the effects of dark matter indirectly, through motion and curvature, but it cannot show dark matter itself. The messenger reaches a wall and stops. Beyond that wall, other messengers are needed. This highlights an important point. Light does not reveal reality directly. It reveals interactions. If there is no interaction, there is no message. Another limit comes from the fact that light always arrives late. Even though it moves extremely fast, it does not move infinitely fast. Every photon you receive left its source earlier, sometimes earlier by fractions of a second, sometimes earlier by billions of years. This delay is not usually noticeable in everyday life, but at larger scales it becomes unavoidable. When you look at the sun, you see it as it was several minutes ago. When you look at distant galaxies, you see them as they were long before Earth existed. Light cannot tell you what is happening right now at a distance. It can only tell you what happened when the light was emitted. The present is always local. Everything else is memory. This means that light cannot provide simultaneous knowledge of distant events. It enforces a kind of loneliness in the universe. Each location experiences its own now. Light connects those nows only after the fact. This is not a technical inconvenience. It is a structural feature of reality. There is no workaround. No better detector can fix it. No stronger telescope can overcome it. Information cannot outrun light. Another boundary appears when you consider resolution. Light has a wavelength, and that wavelength sets a fundamental limit on how finely detail can be resolved. You cannot use visible light to see objects much smaller than its wavelength. The light simply does not interact in a way that preserves fine detail at that scale. This is why microscopes have limits. This is why different wavelengths are used to probe different scales. X-rays reveal atomic structure because their wavelengths are comparable to atomic spacing. Radio waves reveal large-scale structures because they interact over long distances. No amount of clever engineering can bypass this entirely. You cannot force light to reveal details smaller than what its wavelength allows. You must change the light itself. Even then, limits remain. Extremely high-energy photons can probe extremely small scales, but they also introduce new complications. They interact violently. They alter what they observe. They produce cascades of particles that obscure original structures. Light does not offer free access. Every increase in probing power comes with trade-offs. There's also the limit imposed by quantum uncertainty. When light interacts at very small scales, the outcomes are inherently probabilistic. You can predict averages with extraordinary accuracy, but you cannot predict individual events with certainty. This means that light cannot tell you everything about a system at once. Certain pairs of properties cannot be known simultaneously with arbitrary precision. This is not due to poor measurement. It is built into how interactions work. Light carries information, but that information is constrained by quantum rules. You cannot extract more information than the interaction allows. Attempts to do so disturb the system in ways that erase other information. This creates a balance. Light can reveal position, but not precise momentum at the same time. It can reveal energy, but not exact timing beyond certain limits. These are not inconveniences. They are guardrails. They prevent the universe from becoming overdetermined. They allow structure and change to coexist. Another subtle limit arises from interpretation itself. Light delivers raw data, patterns of energy, frequencies, directions, intensities. Meaning is imposed afterward. This means that light cannot tell you what something is in any absolute sense. It can tell you how something interacts with light. Composition, temperature, motion, structure. These are inferred, not directly observed. Even the most sophisticated analysis relies on models, assumptions, context. Light does not carry labels, it carries signals. Understanding those signals requires interpretation. This does not make knowledge unreliable, but it does mean that light never speaks alone. It always speaks through theory. Another boundary appears when light simply cannot escape. In regions of extremely strong gravity, light can be trapped. Once past a certain boundary, light can no longer reach distant observers. Information carried by light is cut off. This does not mean nothing happens beyond that boundary. It means light cannot tell us about it. Events continue, but they are sealed off. This introduces an absolute limit. There are places in the universe that light cannot report on, not because it is blocked, but because the geometry of space-time itself forbids escape. Even closer to home, light can be scattered, absorbed, or scrambled. Dust clouds block visible light, hiding stars and structures behind them. Turbulence distorts signals. Intervening matter alters spectra. These effects can sometimes be corrected for, but not always. Information is lost along the way. Light arrives altered, incomplete. This reminds us that light is not a perfect courier. It is subject to the environment it travels through. It can be bent, delayed, scattered, and transformed. Then there is the limit of perception. Even when light reaches you intact, your senses impose their own boundaries. Your eyes respond to a narrow range of energies. Your brain simplifies, filters, and prioritizes. You never experience raw light. You experience a constructed interpretation shaped by biology and context. Light's message is translated before it becomes awareness. This translation is not neutral. It emphasizes edges, movement, contrast. It suppresses uniformity. It fills in gaps. It creates stability. All of this is useful, but it also means that light alone does not give you direct access to reality. It gives you an interface. Even instruments extend perception rather than replace it. They translate one kind of interaction into another. At each step, assumptions are embedded. There is also the limit of silence. Light only tells us about interactions that occur. It cannot tell us about what did not happen. It cannot report on paths not taken. Possibilities that never became events leave no trace in light. This matters at the quantum level. Many potential interactions exist, but only one outcome occurs. Light records that outcome. The rest vanish without message. This gives light a selective memory. It remembers what happened, not what might have happened. Time compounds this selectivity. As light travels, information spreads out, signals weaken, noise accumulates, details blur. At extreme distances, only the stronger signals survive. Subtle features are lost. The universe speaks more softly the farther back you listen. Even in principle, there are limits to how much information can be extracted from light. Physical laws constrain bandwidth, resolution, and precision. These constraints are not technological. They are fundamental. All of this might sound like a list of disappointments, but it is better understood as a map of boundaries. Knowing where light cannot go tells us where other approaches are needed. Gravity waves, for example, carry information that light cannot. Neutrinos pass through matter almost untouched. Particles reveal interactions light cannot detect. Each messenger has its own domain. Light remains one of the most powerful, but not the only one. This is important for the central question of what light is made of. Light is not a universal key. It is a specific tool. Its composition and behavior define what it can and cannot do. Photons carry energy and momentum. They interact electromagnetically. They obey quantum rules. These properties give them power and impose limits at the same time. Light cannot tell you about everything because it is not everything. It is one way reality communicates with itself, not the only way. Recognizing this prevents overreach. It keeps questions grounded. It reminds us that understanding comes from assembling multiple perspectives, not relying on a single messenger. There is also a quiet philosophical limit here. Light gives us descriptions, not essence. It shows how things behave, not what they are in some ultimate sense. This is not unique to light. It is a feature of all measurement. But because light is so central, its limits stand out. You can analyze light endlessly and still not answer why there is something rather than nothing. Light can tell you how the universe behaves, not why it exists. This does not diminish its value, it clarifies its role. Light is extraordinarily good at revealing structure, change, and relationship. It is less suited to revealing origin, meaning, or necessity. Those questions lie outside its domain. As you rest with this, the idea of limits need not feel restrictive. Boundaries create shape. Without limits, there would be no contrast, no definition. Light's limits help define what kind of universe this is. One where information travels but not infinitely fast. One where observation reveals patterns but not absolutes. One where messengers exist but none are complete on their own. The question sounds simple, almost playful at first. The kind of thing that might be asked half seriously and half as a philosophical tease. Does light exist when no one is watching? It echoes older questions about trees falling in forests and sounds waiting for ears. But when this question is asked about light, it stops being playful very quickly. It reaches into the foundations of how reality is described, how observation fits into physics, and what it means for something to exist at all. At an everyday level, the instinctive answer is yes. Of course, light exists when no one is watching. The sun shines whether or not anyone looks at it. A lamp left on in an empty room continues to glow. Light fills space regardless of attention. Nothing about turning your back makes it disappear, and at one level that instinct is entirely correct. Light does not depend on human eyes. It does not wait for awareness. It does not flicker into being when noticed and vanish when ignored. Photons are emitted, travel, and are absorbed according to physical laws whether or not anyone is present to care. But the question persists because at a deeper level, light behaves in ways that make observation feel strangely entangled with existence. Not in the everyday sense of needing a witness, but in the physical sense that interactions matter. Observation, in physics, is not passive looking. It is interaction. To understand why this distinction matters, it helps to separate two ideas that are often blurred together. One is awareness, the presence of a conscious observer. The other is interaction, the physical process by which systems influence each other. Physics cares about the second, not the first. Light does not require awareness to exist, but it does require interaction to be defined. A photon is not a tiny glowing bead moving through space with a clearly defined position at every moment. Between emission and absorption, its description is spread out, probabilistic. It is not located at a single point in the way a stone is located on the ground. Its existence during that interval is described by a mathematical object that encodes possibilities rather than facts. This does not mean the photon is imaginary or unreal. It means its reality is not object-like during that phase. It is real as a set of potential interactions. When a photon is emitted from a source, that emission is a real event. When it is absorbed by a detector, that absorption is a real event. In between, there is no fact of the matter about where the photon is, only a set of probabilities describing where it could interact if something were there. So when asking whether light exists when no one is watching, the answer depends on what you mean by exist. If you mean, are photons being emitted, propagating according to physical laws and capable of interacting, then yes, absolutely. All of that happens whether or not there is an eye, a mind, or a detector. If you mean, does light have definite properties independent of interaction, then the answer becomes more subtle. Consider an experiment where a single photon travels toward a screen with two openings. If no attempt is made to detect which opening it passes through, the photon's behaviour is described by a wave-like spread of possibilities, and an interference pattern emerges over time. If a detector is placed to determine which opening the photon uses, the interference disappears. The photon behaves differently. This is often misinterpreted as observation creating reality, or consciousness forcing a choice. That is not what is happening. The change comes from interaction, not awareness. The detector interacts with the photon, altering the conditions under which it evolves. The photon does not change because it is being watched. It changes because it is being interacted with in a way that removes certain possibilities. This distinction is crucial. Physics does not require a mind to collapse probabilities. It requires an interaction that makes alternatives distinguishable. Any physical system capable of recording information can play this role. A detector, a molecule, a grain of dust. So does light exist when no one is watching? Yes, but it does not exist as a single, definite outcome until interaction occurs. This may feel unsatisfying if existence is equated with definiteness, but that equation is a habit, not a law. At small scales, reality does not offer definiteness for free. It offers structured possibility. Light exists as a field of potential interactions filling space. It exists as energy capable of being transferred. It exists as a messenger waiting for a recipient. What it does not do is commit to a single story before the interaction demands it. This is not unique to light. Other quantum entities behave the same way. Electrons, atoms, even larger systems under the right conditions exhibit this behavior. Light simply makes it more obvious because it is so familiar and so central. At larger scales, this subtlety disappears. When enormous numbers of photons are involved, interactions happen constantly. Possibilities collapse almost immediately. Definiteness emerges rapidly. A beam of light looks solid. A room looks illuminated. There is no sense of ambiguity. This is why everyday intuition works so well. The world around you is bathed in interactions. Nothing is left in a purely probabilistic state for long. Reality appears firm because it is constantly being reinforced by countless exchanges. But in the quiet spaces between interactions, light behaves differently. If a photon travels through empty space for millions of years before encountering anything, does it exist during that time? Physically, yes. Its quantum state evolves. Its energy remains defined. Its ability to interact remains intact. But there is no event to point to, no record being made, no outcome occurring. In that sense, light exists without happening. This idea challenges the assumption that existence must always be event-like, that something must be doing something to be real. Light shows that something can exist as readiness, as potential, as structure waiting for interaction. This also helps clarify why the universe does not require observers to function. Stars shine without witnesses. Galaxies collide in darkness. Light travels through vast regions of space where no detectors exist. Those photons are not imaginary. They shape environments. They heat dust. They ionize gas. They influence dynamics. Even when no eye sees them, they interact with something eventually. The universe is not paused in the absence of observation. It is active, busy, evolving. The confusion arises because in quantum physics, observation has a technical meaning that overlaps awkwardly with everyday language. Observation means interaction that produces a record. It does not mean awareness, intention, or consciousness. When a photon is absorbed by an atom, that is an observation in the physical sense. Information has been exchanged. A definite outcome has occurred. No mind is involved. This reframing dissolves much of the mystery. Light does not need to be watched. It needs to be interacted with to produce events. The deeper question then becomes whether properties exist independent of interaction. Does a photon have a position before it is detected? Does it have a path? Does it have a definite history? According to the best current descriptions, these questions do not have answers in the way we expect. Not because the answers are hidden, but because the questions are mismatched to the structure of reality. Position is not an intrinsic property of a photon between interactions. It is a property of an interaction. Path is not something a photon carries. It is something inferred after the fact. This does not make light less real. It makes reality less object-centered. Instead of imagining the universe as filled with tiny objects carrying fixed properties, it becomes more accurate to imagine it as filled with processes, interactions, and relationships. Light fits naturally into this picture. It is a process that links events, not an object that persists unchanged. In this view, asking whether light exists when no one is watching is like asking whether a conversation exists before someone listens. The answer depends on what you mean by conversation. The potential is there, the structure is there, the interaction completes it. Light exists as a capacity to interact. Watching, in the physical sense, is what turns that capacity into an outcome. This does not mean that reality is subjective or dependent on minds. It means that reality at small scales is relational. Properties emerge through interaction. At larger scales, this relational nature is hidden by constant interaction. The world looks solid, definite, and independent. But beneath that surface, the same rules apply. Light does not flicker in and out of existence depending on attention. It does not wait for permission. It does not ask to be noticed. It follows laws that allow for potential without commitment. This has an interesting consequence for how we think about knowledge. What we know about light is always tied to how we interact with it. Measurements reveal outcomes, not hidden states. Light tells us what happened, not what might have happened. There is no privileged perspective from which light's full story can be seen all at once. Each interaction reveals one aspect. The rest remain possibilities that never become facts. This does not mean the universe is incomplete. It means completeness does not mean determinacy at every moment. As you sit quietly now, light continues to move around you. Some of it reaches your eyes. Some of it warms surfaces. Some of it passes through walls and bodies without noticeable effect. Most of it never interacts with you at all. All of it exists in the sense that physics requires. None of it requires your awareness. The idea that observation creates reality is a misunderstanding. Interaction creates events. Awareness interprets them. Light exists whether or not anyone is watching, but it does not exist as a finished story until something listens. This perspective does not diminish reality. It makes it more subtle. It allows for a universe that is active, structured, and lawful even in silence. If light exists independently, yet our experience of it depends on interaction, what does that say about our place in the story? Not as creators of reality, but as participants, as receivers of messages that have been travelling long before we noticed them, and will continue long after we stop watching. There is a certain quiet that arrives when questions stop demanding answers and begin to feel more like companions. They do not leave, they simply settle into the background, present without pressure. The question of light, what it is made of, how it behaves, how it connects things across distance and time, eventually reaches that state. Not solved, not closed, just understood enough to stop pulling at the mind. Light, after all this exploration, no longer feels like a thing you need to pin down. It feels more like a condition you are already inside. Right now, light is doing what it has always done. It is moving, it is interacting, it is transferring energy in small, precise amounts. Some of it is reaching your eyes, some of it is warming surfaces, some of it is passing through space without leaving any trace that matters to you. None of this requires effort. None of it requires attention, and yet, without light, none of this moment would feel the way it does. Understanding light does not mean holding every detail in your mind. It does not mean remembering equations, terms, or historical debates. It means having a softer sense of how things fit together, a sense that what appears simple often rests on deep structure, a sense that reality can be both precise and strange without being hostile or chaotic. Light is energy, but not energy that stays put. It is made of photons, but photons are not objects you could collect or stack. It behaves like a wave when it moves and like a particle when it interacts, not because it is confused, but because those are the best tools available for describing different aspects of the same process. Light touches space, bending with it. Light touches time, revealing that it does not flow the same everywhere. Light carries information, but only about what it interacts with. Light exists whether or not it is noticed, but it only becomes experience when something receives it. None of these ideas cancel each other out. They layer. The temptation, especially in science, is to look for a final description, a single sentence that explains what light really is once and for all, but light resists that kind of closure. Not because it is unknowable, but because it sits at the intersection of many rules at once: energy, motion, probability, interaction, geometry. It is not one thing pretending to be many. It is many things expressing one structure. That structure does not demand constant attention. It does not require belief. It simply operates. The universe uses light as one of its ways of staying connected to itself, and you are part of that network whether you think about it or not. Your eyes, when open, receive a narrow band of this activity and translate it into something meaningful. Colour, shape, depth, movement. When your eyes are closed, light still exists, still moves, still touches surfaces and bodies, still participates in countless interactions that do not need to rise into awareness. Understanding this can feel grounding rather than unsettling. It means the world is not fragile. It does not depend on observation to hold together. It is active, structured, and patient. Light does not rush. Even at its immense speed, it follows rules that ensure consistency. It does not arrive early. It does not arrive late. It arrives when it arrives, carrying exactly the energy it carries, no more and no less. There is something steady about that. When people talk about light as illumination, they often mean clarity, knowledge, explanation. But light does not flood everything with answers. It reveals selectively. It highlights some structures and leaves others hidden. It gives enough information to navigate, not enough to overwhelm. This selective quality mirrors understanding itself. You never hold all of reality in your mind. You hold enough to function, to wonder, to rest. The exploration of light shows that not knowing everything is not a failure. It is a boundary condition. Light itself has limits, and those limits shape what kind of universe this is. A universe where information travels, but not infinitely fast. Where interactions are precise, but outcomes are probabilistic. Where structure exists without needing constant confirmation. This kind of universe leaves room for stability and change at the same time. As you sit with this, the glow around you may feel a little different. Not brighter, not dimmer, just quieter. Less like a tool and more like an environment. Light as something you are inside, rather than something you look at. The surfaces in the room are not producing colour on their own. They are participating in exchanges. The air is not empty. It is full of passing signals. The space between objects is not nothing. It supports movement, interaction, and connection. None of this requires effort to maintain. It is already happening. Understanding light does not pull you away from rest. It can support it. There is no need to keep thinking actively. The ideas can remain present without being worked on, the way background light remains present without demanding focus. Even the most complex descriptions of light reduce in practice to something very simple. Energy moves, interactions happen, structures persist long enough to matter. You do not need to picture photons or fields to benefit from their existence. You already do. This perspective can soften the urge to resolve everything. Some questions are meant to remain gently open, not because they lack answers, but because their answers are distributed across many layers of understanding. Light is like that. It is not a single answer. It is a set of relationships that hold consistently. and those relationships are stable. They do not depend on your memory. They do not require vigilance. They do not change because you stop thinking about them. The universe does not forget how light works when you rest. As the pace of thought slows, it becomes easier to notice how little is required of you right now. You're not responsible for maintaining coherence. You're not responsible for understanding everything correctly. You're simply present in a system that continues on its own. Light continues to arrive. Energy continues to move. Time continues to unfold in its uneven way. Space continues to hold patterns and distances. None of this needs supervision. This can be reassuring. The question that started this journey, what is light made of, no longer needs to be answered directly. It has been approached from many angles. It has been loosened from rigid expectations. What remains is a sense of structure rather than a definition. Light is made of energy, organized in specific ways. It is made of interactions that occur in discrete steps. It is made of fields that support motion without substance. It is made of rules that connect space, time, and change. And it is made of relationships that do not require awareness to exist. That is enough. There is no need to conclude anything here. No need to summarize or wrap up. Light does not conclude. It continues. It reflects. It scatters. It passes through. It is absorbed and re-emitted, endlessly reshaping without ever stopping. Understanding can do the same. It does not have to finish. It can simply rest. So you can let the ideas remain where they are, loosely held, not demanding further work. The glow around you does not need explanation. It only needs to be what it already is, and whatever comes next, whatever direction attention drifts, light will still be there, doing what it has always done, quietly connecting one moment to the next without asking anything in return.